On the cold morning of the 25th of December 2021, a golden machine began its journey to reshape humanity's understanding of the universe. From the Guiana Space Centre in French Guiana, an Ariane 5 rocket lifted off, carrying the most ambitious astronomical instrument ever built, the James Webb Space Telescope. If you're fascinated by the mysteries of distant worlds and the search for life beyond Earth, subscribe now. Our journey to uncover the cosmos's hidden secrets begins today. Unlike its legendary predecessor, the Hubble Space Telescope, which circles Earth at a modest 547 kilometers, the James Webb Space Telescope was built to venture far beyond our planet's reach. Its destination, Lagrange Point 2, or L2, a point in space 1.5 million kilometers away, roughly 4 times the distance to the Moon. This isn't just a location, it's a gravitational sanctuary where the pull of the Sun and Earth balance perfectly. A spacecraft here remains aligned with Earth as both orbit the Sun, requiring minimal fuel to maintain its position. Quiet, dark, stable, an ideal perch for the most ambitious observatory humanity has ever built. At L2, Webb wouldn't simply look at the stars. It would capture light that began its journey billions of years ago, unlocking cosmic history encoded in faint infrared signals. But infrared light is delicate. Even the faint warmth of the telescope itself could overwhelm it. Engineers solve this with a marvel of materials science, a 5-layer sunshield of Captain E-. Each layer is thinner than a human hair, coated with reflective aluminum and doped silicon, and together they form a shield 21, 2 meters long and 14.2 meters wide, roughly the size of a tennis court. The outermost layer, facing the Sun, can reach over 110 degrees Celsius, while the innermost layer, hidden in shadow, plunges to 233 degrees Celsius, just 40 degrees above absolute zero. This staggering temperature difference keeps Webb's mirrors and instruments cold enough to detect the faintest glimmers from the farthest reaches of the universe. At the heart of Webb lies its mirror, a technological masterpiece. Spanning 6.5 meters across, it dwarfs Hubble's 2.4-meter reflector, granting nearly 7 times the light-collecting power. The mirror is composed of 18 hexagonal beryllium segments, each one 0.32 meters wide. Beryllium was chosen for its remarkable stability in extreme cold. Each segment is coated with a 100 nanometer layer of pure gold, less than 1,000th of a millimeter yet. This tiny amount is enough to efficiently reflect infrared light. Altogether, the mirrors contain just 48 grams of gold, less than the weight of a golf ball, yet capable of focusing the light of the universe itself. Behind each segment, precision motors adjust the mirrors in steps smaller than 1/10,000th the width of a human hair, merging all 18 reflections into a single flawless image. By January 2022, Webb completed its deployment. Every hinge, latch, and cable, 344 inches total, functioned perfectly. Folded like a giant origami sculpture during launch, the telescope unfolded seamlessly in space. Its instruments were ready. Webb carries 4 main scientific instruments. The near-infrared camera, or NIRCam, captures light from 0.6 to 5 micrometers, imaging forming stars and the warm atmospheres of exoplanets. It also aligns the mirrors with nanometer precision. The near-infrared spectrograph, NIRSpec, developed by the European Space Agency, doesn't take pictures. It separates light into its individual wavelengths. Using microshutters, no larger than a grain of sand, it can observe up to 100 targets at once, revealing the chemical composition of stars, galaxies, and planets. The mid-infrared instrument, MIRI, extends Webb sensitivity to 28 micrometers, observing the coldest and faintest objects dust surrounding newborn stars, icy comets, and distant exoplanets. To operate, it is cooled to 266 degrees Celsius using a helium cryocooler. Without this extreme cold, its own heat would overwhelm the faint signals it seeks. The Near-Infrared Imager and Slitless Spectrograph, NIRIS, built by the Canadian Space Agency, specializes in exoplanet atmospheres. It measures how starlight filters through a planet's atmosphere during transits, detecting gases like water vapor, methane, and carbon dioxide. Together, these instruments do more than see distant worlds, they analyze them molecule by molecule. By February 2022, Webb was fully operational. To test its optics, engineers targeted HD 84406, a star 241 light-years away. The first images revealed 18 separate points of light, one from each mirror segment. Over several weeks, engineers made minute adjustments until all 18 mirrors aligned perfectly, producing an image with infrared clarity twice that of Hubble. The first public release came in July 2022. Among the images was a deep field of the galaxy cluster SMACS 0723, revealing thousands of galaxies, some whose light began its journey 1 billion years ago. The Carina Nebula appeared in unprecedented detail, exposing star formation previously hidden by cosmic dust. Early spectra included WASP-96b, an exoplanet 1,150 light-years away, where Webb detected water vapor in the atmosphere, a clear demonstration of its ability to measure molecules across unimaginable distances. Over the following year, Webb expanded its observations. From massive gas giants to small rocky worlds orbiting dim red dwarfs, the telescope collected terabytes of data, all stored in the Mikulski Archive for space telescopes for scientists worldwide. By mid-2023, Webb had studied over 100 exoplanets, but one in particular captured attention: K2-18b. Discovered in 2015 by NASA's Kepler K2 mission, K2-18b orbits a red dwarf 124 light-years away, roughly 2.6 times the size of Earth and 8.6 times its mass. It is classified as a sub-Neptune. It orbits just 0.14 astronomical units from its star, 1/7 the Earth-Sun distance, yet remains in the habitable zone due to its dim host. Previous Hubble data hinted at water vapor in its atmosphere, but Webb had the power to confirm it. Between July 2023 and February 2024, Webb observed multiple transits of K2-18b, each lasting 7 hours. The telescope measured minute dimming of the star's light, changes equivalent to a fruit fly crossing a distant spotlight. From these delicate signals, scientists extracted the chemical composition of the planet's atmosphere. They detected methane, carbon dioxide, and faint traces of dimethyl sulfide, a molecule on Earth primarily produced by marine phytoplankton. While not conclusive proof of life, these findings suggested a potentially habitable environment far beyond our solar system. From its post at L2, 1.5 million kilometers from Earth, Webb had achieved what no previous telescope could: reading the chemical fingerprints of a distant world orbiting another star, 124 light-years away. It revealed the composition of planetary atmospheres with unprecedented precision, offering scientists a glimpse into environments far beyond our solar system and opening a window into the diversity of alien worlds. Yet this was only the beginning. With its combination of extreme cooling, precision optics, and advanced instruments, Webb had become more than a telescope, it was a laboratory in space. Poised to explore countless exoplanets, decipher the faint signals of distant atmospheres, and push the boundaries of planetary science, it promised to transform our understanding of the universe and the possibilities of life beyond Earth. The target, K2-18b, in the quiet reaches of Leo, 124 light-years from Earth, a dim red star pulses gently, almost unnoticed, yet in its faint glow circles a world that would ignite astronomers' imaginations. K2-18b This planet first revealed itself in 2015, not through a photograph, but through a subtle whisper, a fleeting dip in the star's brightness, captured by NASA's Kepler Space Telescope during its extended K2 mission. Every 33 days, for just a few hours, the star's light dimmed slightly, a delicate signal almost too faint to detect. It was the unmistakable signature of a transit, a planet crossing the face of its sun, etching its passage across the void in photons and time. Initially, K2-18b seemed like any other addition to the growing catalogue of exoplanets, a distant data point in a vast cosmic census. Yet as astronomers reconstructed its size and mass, it defied simple classification. Measuring 2.6 times the radius of Earth and weighing roughly 8.6 times as much, K2-18b occupied a liminal space too large to be rocky, too small to be a gas giant. It became the archetype of a sub-Neptune, a kind of planet absent from our own solar system. Its mean density, just 3.3 grams per cubic centimetre, hinted at an interior rich in volatiles, oceans shrouded beneath a thick hydrogen-helium atmosphere, layers of water and gas locked in a high-pressure embrace. The red dwarf at the planet's heart, K2-18, was unassuming. Half the size of the Sun, emitting less than 3% of its light, it could easily be overlooked by casual observers. But what it lacked in brilliance, it compensated for in longevity. Red dwarfs burn slowly, steadily, for trillions of years, an eternity in which planets like K2-18b can exist in relative stability. Around such a star, time itself is abundant, offering the conditions for chemical complexity and perhaps, in ways not yet imagined, for life to unfold. K2-18b's orbit is close, just 0.14 astronomical units from its star, roughly 1/7 the distance between Earth and the Sunday. Yet the planet is neither scorched nor frozen. The dim, cool light of K2-18 bathes it in just enough energy to maintain temperate conditions on its outer layers. In astrophysical terms, the planet lies squarely within the habitable zone, a region where liquid water might persist, a key ingredient in life as we understand it. To a human visitor, however, the planet would be hostile beyond comprehension. Its gravity would crush an unprotected body. Its thick, hydrogen-dominated atmosphere would smother terrestrial lungs within moments. And yet, scientists began to question whether habitability required an Earth twin at all. Perhaps it demanded only chemistry, energy, and stability. Perhaps life could emerge under conditions we have not yet fathomed. In 2019, the Hubble Space Telescope, its instruments aged but still precise, turned toward K2-18b during a transit. What it observed was extraordinary, the spectral signature of water vapor in the planet's atmosphere. For the first time, an exoplanet within a habitable zone revealed a molecule so intimately tied to life on Earth. The signal was faint, blurred by Hubble's limited infrared capabilities, yet it ignited the imagination of astronomers worldwide. Beneath the hydrogen sky, what lay hidden? Was it a dense, boiling gaseous envelope, or an ocean trapped under immense pressure, isolated from the universe above? K2-18b had shifted from a mere catalogue entry to an enigma. Each observation, each model, suggested more questions than answers. Researchers debated the nature of its clouds, the depth and composition of its atmosphere, and the potential for high-pressure oceans beneath. Could chemical reactions in those hidden oceans, catalyzed by energy from the star or the planet's own internal heat, be enough to sustain complex processes? The possibilities stretched the imagination, and the tools of observation were only just beginning to probe reality. When the James Webb Space Telescope finally opened its golden eye to the cosmos, K2-18b was a natural first target. JWST's instruments were designed for sensitivity beyond Hubble, capable of resolving molecular signatures with unprecedented clarity. The goal was no longer just to detect water vapor. Scientists aimed to map the planet's chemical fingerprints, methane, carbon dioxide, and other compounds that, on Earth, are associated with living processes. Each transit offered a glimpse into a world that had remained invisible for millennia, teasing out the language of its atmosphere, one photon at a time. Preliminary models suggested dynamic activity in the upper atmosphere, fluctuations in temperature between day and night sides, winds whipping across hydrogen layers, and the possibility of storm systems forming in towering clouds. Deep beneath, the pressures and temperatures may have driven interactions between water and gases, generating chemical gradients that, on Earth, often serve as the engines of life. K-18b was a laboratory of extremes, a planet where the familiar rules of habitability might be rewritten. As more data accumulated, the planet's environmental stability became clearer. The hydrogen-rich atmosphere can shield underlying water layers from stellar radiation, maintaining consistent conditions over billions of years. The red dwarf star provides a steady, low-intensity energy input, allowing chemical processes in the atmosphere and potential oceans to continue without major disruption. This contrasts with planets around more active stars, where flares could remove atmospheres and disrupt chemical evolution. Each observation revealed new uncertainties. K-18b could be a gas-shrouded ocean world, or a planet where high-pressure chemical reactions dominate. Determining whether these reactions could reach biologically relevant complexity is still under study. These questions emphasize the diversity of planetary environments and guide ongoing research into the potential for complex chemistry beyond Earth. The red star of Leo continues its steady pulsation, while K-18b orbits quietly. The planet features hydrogen-rich skies and high-pressure water layers, with extreme surface pressures and active chemical processes. Every 33 days, it transits the star, allowing instruments on Earth to measure its atmospheric composition. Observations continue to reveal details about its chemistry and structure, providing an ongoing opportunity to study a planet with conditions unlike those in the solar system. The habitable zone. The term habitable zone is both scientific and poetic. It is the narrow band around a star where the temperature allows liquid water to exist not so close that it boils away, not so far that it freezes solid. Astronomers call it the Goldilocks zone, where conditions are just right. For the Sun, that band stretches roughly from 0.95 to 1.67 astronomical units. For a dim red dwarf like K-18, it hugs close to the star between 0.11 and 0.18 AU. And right there, almost in the middle, orbits K-18b, completing one full lap every 33 Earth days. Its orbit is nearly circular, ensuring stable temperatures. The planet's equilibrium temperature, based on stellar flux and albedo, falls between 250 and 300 Kelvin, roughly 23 to plus 27 degrees Celsius. Not scorching, not frozen, just possible. But temperature alone does not define habitability. The planet's atmosphere acts as both shield and sculptor of its climate. K-18b's hydrogen envelope, far thicker than Earth's, traps heat efficiently, smoothing out day-to-night extremes. Beneath it, layers of methane and carbon dioxide could further regulate the temperature. Theorists modelling its interior picture a deep ocean, hundreds of kilometres thick, pressurised beneath tens of bars of atmosphere. At such pressures, water remains liquid well above 100 degrees Celsius. Here, at the interface between gas and liquid, strange chemistry could unfold, reminiscent of Earth's early hydrothermal vents. Unlike Earth's yellow sun, K-18 star burns cool and red, yet its light, though dim, is constant. Many red dwarfs are notorious for violent flares, but this one appears subdued. Observations show relatively low magnetic activity, suggesting that K2-18b's atmosphere could survive for billions of years without being stripped away by radiation. If life needs time, then this world has plenty. Still, K2-18b's environment differs greatly from Earth. Sunlight passing through its dense hydrogen and methane clouds would appear redshifted and diffuse. If oceans exist, they would be deep and pressurized, with temperatures maintained by the thick atmosphere. These conditions create a stable environment for chemical reactions, providing long timescales for prebiotic chemistry. Such characteristics make K2-18b an important subject for studying atmospheric dynamics, ocean-atmosphere interactions, and planetary heat distribution. Hycean worlds like this expand our understanding of habitability. By analyzing K2-18b's atmosphere and interior, scientists can refine models of planetary climate, chemistry, and energy transfer in non-Earth-like environments, improving criteria for identifying potentially habitable exoplanets. K2-18b's habitability is not merely theoretical, it is a product of its dynamic and complex system. The hydrogen-rich atmosphere acts like a thermal blanket, distributing heat around the planet. Even if the planet is tidally locked one side facing the star perpetually, the other in darkness, the thick atmosphere would transfer energy from day to night, preventing either hemisphere from becoming inhospitably extreme. Beneath the clouds, chemical processes could mirror the earliest reactions that preceded life on Earth. Hydrogen, carbon, and nitrogen molecules interact under high pressures, creating gradients of energy and reactivity. Oceans under tens of kilometers of water and gas could host chemical networks that slowly grow in complexity. These are not oceans in the traditional sense. They are heavy, high-pressure reservoirs capable of sustaining reactions unimaginable on Earth's surface. Red dwarfs like K2-18 burn slowly and steadily. Unlike many of their kind, which unleash violent flares that strip atmospheres from nearby planets, this star is gentle, its magnetic activity muted. This stability ensures that K2-18b's hydrogen envelope remains intact, preserving the environment and giving chemistry and, potentially, life time to evolve. In the cosmic sense, this world has the gift of patience. The alien nature of K2-18b extends to light, color, and perception. Sunlight, filtered through thick hydrogen and methane clouds, would produce muted, surreal hues. Shadows blur, and horizons shift in odd ways. The ocean's surface, if present, reflects this filtered red light, glowing faintly with thermal emissions from the depths below. Life, if it exists, would operate under conditions humans can scarcely imagine. High pressures, dense atmospheres, and light that is dim yet persistent. Scientists have coined a term for such worlds: Hycean planets. Derived from hydrogen and ocean, the classification captures the essence of these sub-Neptune planets, with vast liquid reservoirs hidden beneath hydrogen envelopes. They are not Earth-like in the conventional sense, but they expand the definition of habitability. Life may not require a thin, nitrogen-rich atmosphere or temperate continents. It may only need chemistry, energy, and time, all of which K2-18b has in abundance. K2-18b's orbit also influences its climate in subtle ways. Tidally locked or not, the interaction of the planet's rotation, atmosphere, and potential oceans creates complex patterns of circulation. Winds could swirl in enormous planetary-scale currents, while heat from the star spreads across the globe. The planet's climate, though alien, could be remarkably stable, fostering chemical and perhaps biological processes over eons. K2-18b's atmosphere and potential oceans produce measurable effects. Infrared spectroscopy can reveal water vapor, methane, and carbon dioxide in the hydrogen envelope. Atmospheric circulation, cloud coverage, and temperature gradients can be tracked through transits and phase curves. Studying these observable phenomena allows astronomers to test models and improve predictions for sub-Neptune planets, providing concrete data on climate stability and chemical processes under high pressure. K-18b demonstrates the progress of exoplanet science, from detection to detailed atmospheric characterization with JWST. Its hydrogen envelope, potential subsurface oceans, and stable orbit provide opportunities to study planetary habitability beyond Earth-like conditions. Ongoing observations aim to measure atmospheric composition, thermal structure, and chemical processes. By studying K-18b and similar Hycean worlds, astronomers can expand the catalogue of planets with liquid water, improve understanding of diverse habitable environments, and refine criteria for detecting signs of life elsewhere in the galaxy. The mystery of Hycean worlds. In 2021, researchers from the University of Cambridge proposed a new planetary Category 1 that could fundamentally alter how we think about habitability. They called these Hycean worlds, a name derived from hydrogen and ocean. The term was simple, yet it hinted at something profound. Planets cloaked in thick hydrogen atmospheres, hiding vast, possibly life, bearing oceans beneath. The idea emerged from a striking realization. Many exoplanets discovered by NASA's Kepler and TESS missions occupied a perplexing size range too large to be rocky, yet too small to be gas giants. Planets between roughly 1.5 and 4 Earth radii were becoming increasingly common, yet for decades, scientists dismissed them as inhospitable mini-Neptunes. Their dense hydrogen envelopes, extreme pressures, and high temperatures seemed to rule out life as we know it. But by 2021, new models suggested that these planets might be far more interesting than previously imagined. The key lay in atmospheric composition. Hydrogen, though light, is an excellent insulator. In a planet with the right balance of atmospheric density and greenhouse gases, a hydrogen-rich envelope could trap heat efficiently, keeping liquid water stable beneath clouds. In other words, these were not scorched gas spheres. They could sustain oceans, protected from the cold of space, even around dim stars. Such conditions dramatically expand the classical habitable zone. For an Earth-like planet around a Sun-like star, the habitable zone is narrow, roughly 0.95 to 1.67 astronomical units. But a Hycean world orbiting a dim red dwarf, like K-18, could support liquid water even at a fraction of that distance, sometimes closer or farther than standard models would allow. Hydrogen acts as a thermal buffer, allowing surface, or more accurately, subsurface temperatures to remain within a range suitable for chemistry, and possibly biology, to persist. K-18b became the prototype of this emerging class. Its radius, 2.6 times that of Earth, and its mass, about 8.6 Earths, placed it squarely in the sub-Neptune regime. Its orbit, 0.14 AU, from a cool red dwarf, exposed it to only a fraction of the stellar energy Earth receives, yet its thick hydrogen envelope would act as a blanket, maintaining moderate temperatures. Calculations suggest equilibrium temperatures ranging from 250 to 300 Kelvin, sufficient to allow liquid water under the right pressures. Models of its interior hint at oceans hundreds of kilometers deep, compressed under tens of bars of atmospheric pressure. At these pressures, water remains liquid even at temperatures well above 100 degrees Celsius, a world unlike anything on Earth, yet theoretically habitable. But Hycean worlds also pose profound challenges. Their dense atmospheres scatter and absorb light, obscuring the planet's surface. Spectral features of interest, signs of gases or chemical activity, are difficult to detect. Water, methane, ammonia, and carbon dioxide may exist in supercritical forms, where distinctions between liquid and gas disappear. Under these alien conditions, could life arise? Could complex chemistry persist long enough to evolve? And if life exists, how would it interact with such an extreme environment? Cambridge researchers proposed one potential answer: biosignatures. On Earth, marine microbes release trace gases like methane CH4 and dimethyl sulfide DMS into the atmosphere. In a Hycean ocean, analogous processes could inject detectable compounds into the overlying hydrogen envelope. If observed from afar, these molecules might serve as indirect evidence of life. Detecting them, however, requires instruments capable of distinguishing minute spectral fingerprints against the overwhelming backdrop of hydrogen absorption. That is where the James Webb Space Telescope became revolutionary. Launched with unparalleled infrared sensitivity, JWST could probe the spectra of planets like K2O-18b during transit. By measuring the slight absorption of starlight at specific wavelengths, astronomers could infer the presence of water vapor, methane, carbon dioxide, and even more complex molecules. For the first time, a Hycean world transitioned from theoretical speculation to observational reality. In mid-2023, K2-18b became JWST's first major exoplanet target for this purpose. Observers focused on multiple transits, recording variations in infrared light as the planet passed in front of its star. Early results confirmed the presence of water vapor in the upper atmosphere, a landmark discovery. But JWST's instruments were poised to go further. Beyond water, they sought the subtle signatures of organic chemistry, gases that, on Earth, are produced almost exclusively by living organisms. Even with water confirmed, questions remained. Was the ocean truly global, or trapped beneath localized layers of hydrogen-rich clouds? Did the planet's hydrogen envelope permit stable liquid layers over geological timescales, or were its conditions transient? And perhaps most tantalizing, could life exist in environments so alien that the very concept of habitability must be redefined? Hycean worlds, once theoretical curiosities, are now recognized as an important focus of astrobiology. They expand the range of planetary environments that may support liquid water and complex chemistry, demonstrating that habitability is not limited to Earth-like rocky planets in narrow orbital zones. Studying these planets provides insight into how atmospheric composition, planetary size, and stellar type interact to create stable conditions for water and potential life. By examining K2O-18b and similar exoplanets, scientists can test models of planetary structure and atmospheric dynamics under conditions very different from those on Earth. K2O-18b's place in this narrative is emblematic. Its discovery, characterization, and potential for biosignature detection exemplify how far exoplanet science has advanced in just a few decades. From faint dips in starlight recorded by Kepler to the precise infrared measurements of JWST, each step transforms our understanding, turning speculation into data. Ongoing observations and spectral analysis continue to refine our understanding of Hycean planets. Current models suggest these worlds may be abundant, possibly numbering in the tens of billions within the Milky Way. Each detected Hycean planet, including K2O-18b, offers an opportunity to study the chemistry of dense hydrogen-rich atmospheres and subsurface oceans. Detecting trace gases such as methane or dimethyl sulfide in their atmospheres could provide concrete evidence of chemical processes similar to those driven by life on Earth, advancing our understanding of where and how life might arise in the galaxy. K2O-18b exemplifies the progress of exoplanet science over the past decades. From initial detection by Kepler to detailed spectral analysis with JWST, this planet demonstrates the ability of modern instruments to probe the atmospheres and potential habitability of distant worlds. Future observations will continue to measure its atmospheric composition, thermal structure, and potential biosignatures, providing critical data for models of planetary habitability. Studying K-18b and other Hycean worlds will expand the catalogue of known exoplanets capable of supporting liquid water, helping astronomers evaluate the diversity of habitable environments across the galaxy. JWST's observation campaign. By the summer of 2023, the James Webb Space Telescope had settled into routine operations at the far edge of Earth's gravitational influence, nearly 1 million miles away at L2. Its golden mirrors, composed of 18 hexagonal segments, aligned with painstaking precision, glinting faintly against the darkness of space. These mirrors, cooled to a frigid 40 Kelvin, were now trained on a faint red star in the constellation of Leo. Across the vast distance of 124 light-years, JWST was poised to witness a phenomenon invisible to the naked eye: the passing of K-18b across its star. The observational campaign was meticulously scheduled, stretching from July 2023 to February 2024. It would span several of the planet's 33-day orbits. Each cycle demanded precise timing. Astronomers had to know the minute when the transit would occur, because the window during which starlight passes through the planet's atmosphere lasts only about 7 hours. During this interval, an almost imperceptible fraction of light filters through K-18b's hydrogen envelope, carrying encoded information about the molecules it encounters. JWST's instruments were ready for this challenge. The Near-Infrared Spectrograph, NIR-SPEC, and the Near-Infrared Imager and Slitless Spectrograph, NIRIS, operated in tandem, dissecting the incoming light between 1 and 5 micrometers. These wavelengths are particularly rich in molecular absorption bands. Every molecule leaves a distinct spectral fingerprint. Methane absorbs at 1.6, 5 and 3.3 micrometers, carbon dioxide near 4.3 micrometers, water vapor across multiple bands from 1.4 to 2.7 micrometers. Even minor constituents, like ammonia or hydrogen cyanide, produce subtle imprints detectable only through high-resolution spectroscopy. The data from each transit stream down to Earth as intricate numerical arrays. Each line represented the faintest dip in brightness across thousands of wavelength channels. For a single transit, a difference of 1 part in 10,000 could reveal the presence of a molecule thousands of light-years away. Scientists could reconstruct the atmosphere of K-18b, its composition, its pressure layers, and even hints of its temperature profile without ever leaving Earth. But gathering photons was only the beginning. JWST's detectors are exquisitely sensitive, meaning that instrumental noise, cosmic rays, and thermal fluctuations all had to be identified and removed. Calibration demanded layers of modelling, including flat field correction, dark current subtraction, and Poynting jitter analysis. Bayesian retrieval frameworks were then applied, testing millions of simulated atmospheres against the observed spectrum. Each iteration refined estimates of temperature, pressure, and molecular abundance, providing a probabilistic map of the planet's upper layers. Expectations were high. Hubble had already glimpsed water vapor in the atmosphere of K-18b, but its infrared reach was limited. JWST extended that vision, offering not only deeper penetration, but also the ability to quantify molecular ratios with unprecedented precision. With every transit, the infrared data revealed peaks and valleys corresponding to absorption by gases high in the atmosphere. Methane appeared at multiple bands, carbon dioxide left broad troughs, and water produced complex overlapping features. Each molecule was a thread in the chemical tapestry of a distant world. The observational campaign unfolded as a meticulous layering of knowledge. Over 7 months, JWST captured multiple transits, each reinforcing and refining previous measurements. Atmospheric signatures that had been faint or ambiguous in a single transit emerged clearly when the data were co-added. Seasonal variations of the star and minor instrumental effects were accounted for, ensuring that the signals truly belonged to the planet, not artifacts of observation. Among the expected molecular markers, however, something unusual emerged. Narrow, weak features appeared that resisted classification. They were too structured to be random noise, too persistent to be dismissed. When analysed separately, they recurred across different instruments and transits, suggesting the presence of molecules not commonly found in planetary atmospheres as we know them. Data reduction teams at NASA's Goddard Space Flight Centre, the University of Cambridge, and the Canadian Space Agency initiated independent verifications. Each team applied distinct calibration algorithms, cross-checked with synthetic spectra, and compared against known molecular databases. Statistical significance was assessed rigorously, with Monte Carlo simulations confirming that the anomalies were unlikely to be random. If these features held up, they could indicate chemical processes previously observed only on Earth, or perhaps entirely new atmospheric chemistry. JWST's precision was critical. Its detectors measure photons with part per million accuracy, and its infrared capability spans the critical bands for water, methane, carbon dioxide, ammonia, and trace organic molecules. By comparing the depth and shape of absorption lines, scientists could estimate not only the presence, but the concentration of gases, creating a three-dimensional map of K2O-18b's upper atmosphere. Variations in line broadening and shifting provided indirect evidence of temperature gradients, atmospheric circulation, and even high-altitude winds. The campaign also benefited from international collaboration. Observatories on Earth monitored K2O-18's photometric variations to track star spots and minor flaring activity, ensuring that any changes in starlight were planetary, not stellar. Coordinated data processing pipelines allowed cross-validation of results, increasing confidence in the emerging spectral fingerprints. By mid-2024, the accumulated observations had produced the most detailed infrared spectrum ever captured for a sub-Neptune exoplanet. As each transit passed, JWST captured new layers of detail, peeling back the atmosphere of K2O-18b bit by bit. The planet's faint shadow moved across its star, revealing distinct absorption signatures from methane, carbon dioxide, and water vapor. Unexpected spectral lines, though weak, repeated across multiple transits, suggesting something new was at play. Instruments ran continuously, recording precise infrared data, tracking even the slightest fluctuations in starlight. Every observation added a fresh piece to the puzzle, and with each new measurement, the team gathered more evidence to refine their understanding of this distant world's atmosphere. By the time the campaign concluded, a rich dataset had been compiled, mapping K2O-18b's atmosphere in unprecedented detail. NIRSpec and NIRIS instruments tracked subtle shifts in spectral lines, capturing atmospheric variations across multiple orbits. Each new transit added a layer of clarity, from chemical composition to temperature gradients. The data was organized meticulously, ready for analysis. With every bit of information, the picture of K2O-18b's atmosphere grew sharper, and the team stood poised to reveal the hidden dynamics of this alien world. The spectral fingerprints. Every molecule has a signature. Methane bends and stretches in a pattern of infrared frequencies. Carbon dioxide vibrates differently, absorbing light at distinct bands. To read a planet's spectrum is to read its invisible handwriting, tracing the unseen chemistry of a distant world. When JWST's data for K2O-18b was finally reduced and cleaned, the first features to stand out were unmistakable: methane CH4 and carbon dioxide CO2. These gases absorb strongly in the near-infrared, producing broad dips in the spectral curve, at roughly 3.3 micrometers for methane and 4.3 micrometers for carbon dioxide. Each peak and trough represented the interaction of light with molecules thousands of trillions of kilometers away, captured as digital imprints by the observatory's sensitive detectors. The presence of both gases together was immediately intriguing. In hydrogen-dominated atmospheres, such a combination can indicate thermochemical disequilibrium conditions that require active maintenance by internal processes. On Earth, disequilibrium is a hallmark of life. Oxygen and methane coexist because of the continuous output from living organisms. To a scientist, that word disequilibrium is electric. It signals energy flowing, chemistry that refuses to settle, and dynamic processes far from static equilibrium. JWST's spectra, however, offered more than just the expected molecules. Between 3.4 and 3.6 micrometers, faint, narrow absorption notches flickered, barely above the noise threshold. These subtle dips didn't correspond to any simple, well-known atmospheric gas. At first, the team suspected instrumental contamination, cosmic rays, detector quirks, thermal drift, but repeated observations across multiple transits told a different story. As reprocessing continued, the same pattern emerged consistently. Cross-checks between independent data reduction pipelines confirmed the persistence of these faint features. They were small, almost imperceptible, but they refused to vanish. The persistence alone transformed what could have been a statistical fluke into a genuine signal worth investigating. Researchers then expanded their molecular library. They compared the data against databases containing thousands of potential infrared absorbers: ammonia, ethane, acetylene, sulfur compounds, nitriles, and dozens more. Slowly, one candidate began to fit the pattern: dimethyl sulfide, or DMS. On Earth, DMS is a product of life. Marine phytoplankton release it as part of their sulfur metabolism, a process that indirectly influences cloud formation and contributes to the familiar smell of the ocean. Detecting it on another world, hundreds of trillions of kilometers away, would be staggering, perhaps the first chemical hint of biology beyond our solar system. But the team approached the finding with extreme caution. Extraordinary claims require extraordinary evidence. They revisited every stage of the analysis. Calibration lamps were rechecked, detector persistence and drift were reassessed, cosmic ray impacts were re-examined, and noise models were rigorously tested. Atmospheric simulations were run for a range of pressures, temperatures, and altitudes. In each scenario, the DMS-like feature persisted. The story didn't end there. Beyond DMS, a secondary pattern began to emerge, one weaker yet consistent across multiple transits. It matched the spectral signature of dimethyl disulfide, DMDS, another sulfur-bearing organic molecule intimately linked to sulfur cycling on Earth. The combination of DMS and DMDS was particularly tantalizing because no known abiotic reaction in a hydrogen-rich atmosphere would easily generate both in measurable quantities. Scientists refrained from labeling it as life. The term anomalous chemistry was used to describe the unusual observations, allowing room for further investigation. This term captured the complexity of the data without jumping to conclusions. Still, the implications were impossible to ignore. The atmospheric ratios, the consistency of the features across multiple datasets, and their correlation with molecules related to biological processes suggested a chemical environment more complex than previously observed. Each transit revealed slight variations in absorption depth, indicating dynamic atmospheric processes that influenced chemical distribution. JWST's high spectral resolution allowed the team to measure relative abundances with parts per million precision. Methane dominated the upper atmosphere. Carbon dioxide maintained a stable background presence, and trace organosulfur compounds hovered at the detectable edge. Modeling these ratios suggested active replenishment, an ongoing source of molecules rather than a one-time chemical accident. Temperature and pressure profiles further complicated the narrative. K2-18b's hydrogen envelope, though vast and thick, allows the infrared signatures of trace gases to emerge from the middle layers of the atmosphere, hundreds of kilometers above the hypothesized ocean below. These conditions, while extreme by Earth standards, do not preclude complex chemistry. Indeed, theoretical models indicate that DMS and DMDS could persist under moderate ultraviolet flux from the red dwarf star, shielded by the planet's haze and cloud layers. In parallel, the team explored alternative explanations: volcanic outgassing, lightning-driven chemistry, photochemical reactions in high-altitude hazes. All were simulated. None reproduced the observed pattern convincingly. Abiotic pathways could produce methane and carbon dioxide individually, but the combination of sulfur compounds alongside these gases in the measured ratios defied known planetary chemistry. The spectra also hinted at additional minor features, barely rising above the detection threshold, corresponding to other organics such as ethane and trace nitriles. Each feature added complexity, suggesting the presence of diverse chemical processes. If confirmed, this array of molecules would make K2-18b one of the most complex exoplanetary atmospheres ever observed. The entire process was painstaking. Each dataset required careful vetting. Each analysis had to be repeated across independent teams, and each interpretation had to withstand scrutiny from astronomers across multiple continents. Still, the data revealed clear patterns in absorption lines and photon counts, highlighting both familiar and unfamiliar aspects of the planet's chemistry. While the faint signatures of sulfur molecules raised significant interest, they also underscored the limitations of current methods. Instruments, models, and theories could describe the data with high probability, but direct confirmation of life on K2-18b remained beyond reach. For now, the team could only interpret the spectral data. As each spectral curve was overlaid, refined, and analyzed, a clear pattern emerged. K2-18b's atmosphere exhibited complex chemistry, with gases interacting, persisting, and possibly cycling in ways that could offer insights into its chemical processes. Methane, carbon dioxide, DMS, and DMDS, each line in the spectrum provided a clue to the planet's atmospheric dynamics. For the team, the excitement lay in the precision. Small dips at the edge of the spectrum, just a few parts per million, pointed to new avenues for exploration. JWST had captured the data, and the scientists were now analyzing it to uncover the details of this distant world, molecule by molecule. In the end, the spectrum was more than just data. It was a detailed record of a world, captured in near-infrared light, revealing a planet that defied easy categorization as sub-Neptune, a Hycean world, and a unique example of complex atmospheric chemistry. Dimethyl sulfide, the surprise signal. The confirmation came in early 2024, after months of painstaking cross-analysis. The faint absorption features around 3.4 and 3.5 micrometers in JWST's spectra, first noted as tentative in the previous year, now persisted across independent observations and processing pipelines. Every potential source of error instrument drift, cosmic ray hits, thermal noise, calibration inconsistencies had been meticulously tested, simulated, and ruled out. What remained was stubborn, narrow, and unmistakable. When the numbers were run through Bayesian retrieval models, the statistical significance became clear: 3 sigma. In other words, there was a 99.7% probability that the signal was real. In most scientific disciplines, that level of confidence is considered definitive. But astrophysics, especially in the hunt for exoplanetary biosignatures, is a domain of extreme caution. A single misinterpretation can propagate through entire theoretical frameworks. For the team, 99.7% was a milestone but not a verdict. The team did not claim life. They announced a possible detection of dimethyl sulfide, or DMS, in the atmosphere of K2-18b. On Earth, DMS is produced almost exclusively by marine microorganisms, primarily phytoplankton. The sulfur cycle that generates it involves complex biochemistry. Phytoplankton metabolize sulfur, containing compounds in seawater, releasing DMS as a byproduct, which then participates in atmospheric and cloud chemistry. There is no known geochemical or photochemical pathway that can produce DMS in measurable quantities under conditions similar to those of Earth. If DMS truly exists in K2-18b's hydrogen-rich atmosphere, the implications are profound. It would suggest chemical processes strikingly analogous to Earth's marine ecosystems, cycles of carbon, hydrogen, and sulfur interacting under mild pressures and temperatures. In other words, the planet's atmosphere might harbour processes capable of sustaining complex, possibly lifelike chemistry, in a manner that mirrors our own oceans. Yet the team approached these results with deliberate caution. Alternative sources were systematically tested. Could volcanic outgassing produce sulfur compounds that mimic the DMS signature? Could high-pressure photochemistry in a hydrogen-rich atmosphere generate false positives? Could minute crosstalk between JWST's near-spec and nearest instruments, or subtle calibration drift, produce spurious absorption lines? Each scenario was modelled with painstaking detail. Volcanic scenarios required fluxes orders of magnitude greater than plausible for a sub-Neptune like K2-18b. Photochemical pathways either produced spectra inconsistent with the observed features or required extreme UV fluxes incompatible with the planet's red dwarf host star. Instrumental artifacts were tested using both synthetic and real calibration datasets, and multiple pipelines independently reproduced the same faint DMS-like feature. The conclusion was unavoidable. The signal, narrow and stubborn, persisted. At the University of Cambridge, principal investigator Niku Madhusudan coordinated the international effort to contextualize the findings. In a carefully worded statement, he explained, "This detection does not confirm life, but it does confirm that K2-18b's atmosphere exhibits chemistry far more complex and Earth-like than we anticipated." The phrasing was deliberately restrained, but the astonishment beneath it was palpable. No telescope in history had ever recorded a candidate biosignature on an exoplanet with such statistical confidence. The scientific world recognized the subtle audacity of the claim, a faint whisper of chemistry traveling over 100 light-years, encoded in infrared light, potentially hinting at biological activity. The figure 99.7% confidence circulated rapidly through scientific networks, preprint servers, and social media. For some, the number was enough to spark cautious optimism. For others, even a 1 in 3 7-0 chance of error demanded strict skepticism. The scientific debate was immediate and global. Conferences devoted sessions to modelling abiotic DMS production, while labs ran high-pressure experiments simulating hydrogen-rich atmospheres. Some teams argued for the plausibility of exotic geochemistry. Others emphasized the uniqueness of DMS as a biologically derived molecule. Late in 2024, the Cambridge team submitted their results to the astrophysical journal Letters. The manuscript was meticulous. Data tables extended over dozens of pages, model assumptions were carefully documented, and error propagation was treated with exhaustive detail. Every step of the Bayesian retrieval process was explained, with separate sections dedicated to instrument characterization, cosmic ray mitigation, and cross-validation with independent pipelines. The language of the paper was precise, emphasizing probabilities and reproducibility rather than speculation. When the preprint was released, the scientific community reacted with a mix of awe and restraint. Headlines quickly picked up the story, often exaggerating for dramatic effect. JWST detects life, and a planet with a 99.7% chance of biology. Researchers immediately clarified the nuances. The detection was compelling, but a direct confirmation of life would require corroborating evidence from additional molecules, temporal variability studies, or far in the future, direct sampling. Yet even amid these clarifications, the excitement was tangible. For the first time, a molecule closely associated with life on Earth appeared in an exoplanetary atmosphere with a degree of statistical robustness never before achieved. Further analysis revealed additional subtleties in the spectral data. The DMS feature was accompanied by minor, consistent hints of dimethyl disulfide, DMDS, a related sulfur compound. On Earth, DMDS often forms from the oxidation of DMS, completing a small portion of the sulfur cycle. Its presence on K2O-18b, faint but persistent, added another layer of complexity to the chemical picture. Abiotic models struggle to reproduce both molecules simultaneously in the observed ratios, reinforcing the anomaly. The confidence level remained constant across multiple transits, indicating that these molecules were not transient or spurious. Temporal averaging over several orbital periods allowed the team to construct a vertical profile of the atmosphere, revealing that the organosulfur compounds likely originated from mid-altitude layers, shielded from the strongest ultraviolet radiation by thick hydrogen clouds above. Modeling the vertical mixing suggested continuous replenishment, implying dynamic chemical processes. The detection of DMS also prompted a re-examination of JWST's previous datasets. Researchers compared K2O-18b to other sub-Neptunes observed in 2023. None exhibited the same sulfur chemistry, strengthening the uniqueness of the signal. It became clear that K2O-18b was not just another exoplanet. It was a chemically active laboratory in the sky, revealing processes previously thought improbable in hydrogen-dominated atmospheres. Laboratory simulations of hydrogen-rich atmospheres with trace organosulfur compounds provided additional insights. When methane, carbon dioxide, and DMS were combined under plausible pressures and temperatures, reaction pathways suggested subtle atmospheric feedback mechanisms. Even without life, the chemical network would be unusually active, producing minor spectral features that aligned closely with JWST's observations. This interplay between biology-like chemistry and plausible abiotic reactions kept the scientific discourse rigorous, balancing excitement with caution. The Cambridge team, alongside collaborators at NASA Goddard and the Canadian Space Agency, continued refining their models. Every iteration tested new combinations of gases, temperature gradients, and cloud opacity. Each step brought the spectral fingerprints into sharper focus. Through this iterative process, the faint 3.4 and 3.5 micrometer absorptions became more than just anomalies. They were reproducible signatures, persistent across months of observation. By early 2025, K2O-18b had become one of the most closely studied exoplanets. JWST's data had illuminated the faint signal, and the team's analysis had confirmed its persistence. Dimethyl sulfide, narrow and consistent, remained a key signal, one that prompted further investigations, additional transits, and ongoing searches for potential biosignatures on similar Hycean worlds. The DMS detection remained an intriguing anomaly. The signal was persistent and statistically robust, yet the distinction between biological and abiotic processes was still to be determined. In laboratories, simulations progressed. In telescopes, further transits were monitored. K2-18b's chemical complexity had moved from theoretical to observable, with JWST capturing molecular signatures that invited deeper investigation. What 99.7% means in science. Numbers in science are measures of probability, quantifying certainty and guiding how data is interpreted. When the K2-18b team announced a 99.7% probability that the dimethyl sulfide signal was real, they weren't simply reporting a statistic. They were speaking in sigma levels, the language scientists use to quantify confidence. In astrophysics, a 3 sigma detection carries a very specific meaning. Statistically, it corresponds to roughly a 1 in 370 chance that the signal could arise from random noise. Picture this: if the same experiment were repeated 370 times under identical conditions, a single false positive could appear. That's why scientists speak of 3 sigma, with excitement tempered by caution. It's compelling, but not definitive. By contrast, the Higgs boson discovery in 2012 required 5 sigma, representing a 1 in 3, 5 million chance of a fluke. This has become the gold standard for declaring a discovery conclusive. K2-18b's 3 sigma signal lies between possibility and certainty, strong enough to provoke excitement, yet demanding follow-up. It calls for further examination and scrutiny. Even at 3 sigma, the implications are significant. Dimethyl sulfide, DMS, and dimethyl disulfide, DMDS, faint but persistent, have no known abiotic sources under K2-18b's hydrogen-rich conditions. Their presence challenges current understanding. Could chemical processes akin to those in Earth's oceans exist under alien skies? Could hydrogen-dominated atmospheres support lifelike chemistry? These questions stem directly from the statistical rigor of the detection. Sigma levels provide context, but also underscore the limits of certainty. Consider the photons that travelled 124 light-years to reach JWST. Trillions of kilometres condensed into a few spectral dips on an infrared detector. Our confidence is always mediated by instrument calibration, modelling assumptions, and data interpretation. Yet within these constraints, 99.7% is far from random. It is a strong anomaly demanding attention. For scientists, the number guides action. A 3 sigma detection justifies follow-up campaigns, additional transits, cross-instrument verification, and testing of alternative hypotheses. Every plausible physical, chemical, or biological explanation must be explored. Could high-pressure photochemistry in a hydrogen-rich atmosphere mimic DMS? Could trace volcanic sulfur compounds accumulate to form the spectral signature? Models suggest these scenarios are unlikely, but nothing is dismissed without thorough analysis. The distinction between statistical significance and interpretive certainty becomes clear when comparing DMS and DMDS ratios. On Earth, DMDS forms from DMS oxidation within the sulfur cycle. On K2-18b, their simultaneous appearance persistent across multiple transits adds a layer of complexity that abiotic models struggle to reproduce. This pattern is precisely why the 99.7% confidence level is meaningful. The signal is persistent, structured, and consistent with a dynamic atmospheric process, whether biological or otherwise. Beyond the numbers, sigma framing influences strategy. Scientists prioritize which observations to repeat, which molecules to search for next, and how to model atmospheric processes. Each 3 sigma result provides a roadmap for future research, pointing to chemical pathways, atmospheric layers, and potential biosignatures that warrant exploration. Statistical confidence also intersects with spatial and temporal analysis. The vertical profile of K2-18b's atmosphere, inferred from repeated transits, indicates mid-altitude origins for DMS and DMDS, shielded from UV radiation by hydrogen layers above. This vertical distribution implies ongoing replenishment, a dynamic system rather than a transient anomaly. Understanding such spatial patterns is critical because it informs whether chemical cycles are sustained and potentially life-compatible or merely transient and abiotic. Even subtle spectral hints can carry enormous weight. A single spectral dip corroborated across instruments and transits becomes a data point with profound implications. In laboratories, simulated atmospheres reproduce complex chemical interactions under pressures and temperatures consistent with K2O-18b. Methane, carbon dioxide, and trace organosulfur compounds react in ways that create minor spectral features mirroring the observations. Each alignment between model and observation reinforces the anomaly, tightening the statistical grip of the 3 sigma detection. This kind of detective work becomes the backbone of progress. Scientists dive deeper into the atmospheric models, continuously refining them based on new data, additional spectroscopic features, and feedback from other research teams. They recreate every variable in the lab, ensuring that no stone is left unturned. Are there other, perhaps unknown, geochemical processes that could mimic this signal? Could there be another molecule hiding in the spectrum, causing interference? The careful and persistent examination of these possibilities is what turns a fascinating anomaly into a confirmed lead. In this context, 99.7% is both a measure and a motivator. It defines what can be acted upon, what deserves scrutiny, and what is still tentative. It frames research priorities, drives laboratory experiments, and guides telescope time allocation. It is a signal that says, something unusual is happening here. Investigate. For the K2O-18b team, that meant more than analysing data. It involved iterative modelling, cross-instrument verification, and international collaboration. Every hypothesis, biological, chemical, or instrumental, was challenged, recalculated, and tested. The faint spectral features at 3.4 and 3.5 micrometers persisted, resisting dismissal, and in doing so, demanded attention from the global scientific community. At the frontier of exoplanetary research, 99.7% becomes a tangible benchmark. It is thrilling, precise, and actionable. It allows scientists to differentiate between noise and anomaly, between mere curiosity and phenomena worth chasing. In the case of K2O-18b, it transforms faint infrared dips into a chemical narrative, one that unfolds molecule by molecule, transit by transit, as astronomers seek to understand a world 124 light-years away. By the middle of 2025, the K2O-18b team was looking at data in a new light. The statistical confidence 99.7% had opened doors, inspired new hypotheses, and drawn in the best minds in the field. As independent labs and research teams weighed in, the search for corroborating signals grew more intense. Each subsequent observation added layers of data, further solidifying the case for a chemical process far beyond what was thought possible in a hydrogen-rich atmosphere. The K2O-18b story was no longer just about the detection of a molecule. It was about redefining the chemical potential of exoplanets. New research directions were emerging. Could K2O-18b harbour more Earth-like chemistry than previously imagined? Could these organosulfur compounds DMS and DMDS suggest a chemical cycle that could resemble processes leading to life, or at least a version of chemistry similar to life on Earth? These were the questions now being explored, questions that 99.7% certainty had made possible. Every new transit, every new data point added weight to the case. The team didn't yet have a definitive answer, but they now had a powerful tool, a statistical confidence level high enough to keep pushing forward. The path ahead was clear: more observations, refined models, and, most importantly, more questions. In science, it is the questions that drive the next big discovery. By 2025, the K2-18b team was no longer just observing data. They were following a trail, a statistical anomaly that had become a catalyst for a new chapter in the study of exoplanet atmospheres. The 99.7% confidence level was not an endpoint. It was the spark that ignited deeper investigations into the chemical processes occurring on distant worlds. It was a reminder that in science, certainty is rarely absolute, but the pursuit of understanding continues. The atmosphere of K2-18b. To understand why K2-18b might host life, or at least lifelike chemistry, we must first explore its atmosphere. Not physically, of course, but through the chemical signatures that Webb has transmitted across the vast expanse of space. These data provide a unique window into a world unlike any we've encountered before. The atmospheric composition of K2-18b reveals a strikingly alien environment, one dominated by hydrogen. The planet's hydrogen-rich envelope envelopes a world more than 2.6 times the size of Earth and about 8.6 times its mass. It's a massive, gas-heavy planet with an atmosphere that stretches high into the sky, where molecules drift according to the whims of temperature, pressure, and radiation from its red dwarf star. Within this vast atmosphere, scientists have detected familiar yet intriguing compounds: methane CH4, carbon dioxide CO2, and dimethyl sulfide DMS. Water vapor is likely present in the upper layers, though its signature is entangled with the dense hydrogen, making it difficult to isolate. The presence of water, methane, and carbon dioxide suggests that the planet's atmosphere is dynamic, with complex chemical interactions occurring beneath the dense veil of hydrogen. The atmospheric pressures at the potential ocean interface the boundary between the thick hydrogen envelope and any liquid ocean beneath could reach tens of bars, comparable to the pressure found hundreds of meters underwater on Earth. Temperature estimates range from 250 to 300 kelvins, or roughly 23 degrees Celsius to plus 27 degrees Celsius. This temperature range suggests that liquid water could exist beneath the hydrogen canopy, providing a potential environment for chemistry that might resemble Earth's oceans. But it's not just the temperature and pressure that make K2-18b's atmosphere compelling. It's the unique chemistry at play. On Earth, life exists within nitrogen-oxygen atmospheres, where greenhouse gases are relatively thin and well-regulated. On K2-18b, hydrogen is the dominant gas, creating a potent greenhouse effect. This thick atmosphere traps heat, making the planet much warmer than it would otherwise be, yet it is still transparent enough in the infrared for the James Webb Space Telescope, JWST, to detect molecular signatures, like DMS. What makes the situation even more intriguing is that methane is unstable in an atmosphere exposed to stellar radiation. It tends to break down over time unless it is replenished. On Earth, biology replenishes methane through microbial processes, such as in wetlands or digestive systems. Could something similar be happening on K2-18b? The coexistence of methane, carbon dioxide, and DMS raises the possibility that dynamic processes, possibly biological, are at work, replenishing methane and other gases. If so, this hints at an active, potentially life-supporting chemistry within the planet's atmosphere. Scientists model K2-18b's atmosphere in stratified layers. The upper layers are exposed to stellar radiation, while the middle layers mix via convection. Below these, deeper layers might be in contact with a global ocean, forming a complex atmospheric system where each layer contributes to the planet's spectral signature. It's as though the atmosphere is a multi-layered painting, each layer adding a subtle touch to the overall composition. The detection of DMS in this context implies that somewhere within these layers, chemistry is interacting with water in ways reminiscent of Earth's own oceans, a tantalizing glimpse of a potentially habitable environment. Further adding to the complexity is the fact that K2-18b orbits a red dwarf star, K2-18, which is much quieter than many other M-dwarfs. While red dwarf stars can be highly active, emitting violent flares and high radiation, K2-18 is relatively calm. Its flares are infrequent, and it emits only 2.4% of the Sun's total luminosity, meaning it delivers moderate energy to its planets. This relatively stable environment reduces the likelihood that photochemical reactions would destroy delicate molecules like DMS before they could accumulate. In other words, the conditions on K2-18b are less likely to be ravaged by extreme stellar radiation, which could otherwise erase the chemical signatures scientists are seeing. The combination of these factors, the right temperatures, the right pressures, the presence of water, and the stable radiation from the host star forms a portrait of a world that could plausibly support lifelike chemistry. The chemistry unfolding in K2-18b's atmosphere challenges the old notion that habitable planets must mirror Earth's size, composition, or atmospheric makeup. The presence of hydrogen in the atmosphere, the abundance of methane and carbon dioxide, and the detection of DMS, these are not just data points, they are windows into the possibility of an alien ecosystem, one that could be fundamentally different from anything we've imagined, yet still capable of supporting lifelike chemistry. K2-18b's atmosphere presents an alternative model of habitability. While Earth's biosphere thrives in a nitrogen-oxygen atmosphere, K2-18b's hydrogen-dominated environment could support a form of chemistry that is, if not life as we know it, then something incredibly close. The detection of DMS is a particularly strong indicator of complex processes unfolding in the atmosphere, processes traditionally associated with biological systems. Could this be evidence of an alien biosphere, or are we witnessing an unusual abiotic chemical cycle? The answer is far from clear, but the very existence of these signatures raises a fundamental question. How broad is the spectrum of environments that could support lifelike chemistry? The planet's atmospheric dynamics also provide a unique opportunity for scientists to test the limits of life's adaptability. How far can chemistry stretch before it becomes fundamentally different from what we recognize as life? The methane, the carbon dioxide, and the DMS all suggest a chemical interplay that mirrors, in some ways, Earth's own biogeochemical cycles. Could these compounds exist in an environment so radically different from Earth's and still support complex reactions that could lead to life, or at least lifelike processes? This is the challenge and the thrill of studying planets like K2-18b. It forces us to reconsider the fundamental principles of habitability and to imagine life in forms we might not yet fully understand. As scientists continue to study K2-18b's atmosphere, each new piece of data adds another layer of complexity to the story. The detailed models, the data from JWST, and the continued analysis of the chemical signatures all paint a picture of a planet that is both alien and strangely familiar, a world where chemistry is unfolding in ways that suggest the possibility of life, or at least lifelike processes, in a completely different context than we see on Earth. And the questions keep coming. If we detect lifelike chemistry on K2-18b, what will it mean for our understanding of life in the cosmos? Will this discovery prompt us to rethink what makes a planet habitable? Or will it expand our definition of what life can be, opening new doors to explore the vast diversity of planetary environments that might support the chemical processes we associate with life? For now, the atmosphere of K2-18b remains a tantalizing enigma, its chemical signatures offering glimpses of a potential alien biosphere. But one thing is certain: the hunt for life beyond Earth has entered a new phase, and K2-18b is a central figure in this cosmic exploration. The role of methane and carbon dioxide. The discovery of methane and carbon dioxide on K2-18b introduces a fascinating puzzle. The coexistence of two gases that, on Earth, rarely linger in the same atmosphere without intervention. Methane, a molecule often linked to biological processes, is a stable gas only when replenished, as it tends to break down when exposed to stellar radiation. On our own planet, it's microbes, specifically archaea, that create methane in wetlands, digestive systems, and other environments. But this is not just a terrestrial phenomenon. It's a chemical paradox in the atmosphere of an alien world. K2-18b's atmosphere, rich in hydrogen and shrouded in mystery, shows an unexpected balance. The James Webb Space Telescope, JWST, has detected methane and carbon dioxide in what appears to be a stable ratio, an occurrence that demands a deeper examination. These gases are not simply hanging in the air. They are actively interacting in ways that suggest something is replenishing methane in particular, maintaining a chemical disequilibrium that hints at the presence of some force, natural or otherwise, sustaining the system. The critical question remains: how is this equilibrium being maintained? The presence of methane and carbon dioxide together, in a form that resists natural breakdown, points to a dynamic source, something that is preventing them from disappearing into space or being chemically neutralized. It is this disequilibrium, this struggle between the forces that would drive the two gases into balance, that has researchers intrigued. On Earth, the most likely culprit for such a situation would be life, a living system, constantly replenishing methane through biological processes. But life is not the only explanation. K2-18b is far from Earth, orbiting a red dwarf star with an environment that we are only beginning to comprehend. Volcanic activity, hydrothermal vents, or even photochemical reactions could also produce methane and carbon dioxide. These non-biological processes could create a similar disequilibrium, although the combination of methane, carbon dioxide, and dimethyl sulfide, DMS, along with hydrogen as a solvent, suggests something more complex at play. The combination of methane's absorption band at 3.3 micrometers and carbon dioxide's at 4.3 micrometers gives astronomers a way to track these molecules through the planet's thick, hydrogen-rich atmosphere. When viewed together, they reveal not just the molecules' presence, but the way they shape the planet's thermal dynamics. These interactions influence everything from cloud formation to atmospheric circulation. The planet's albedo, the fraction of sunlight it reflects, versus what it absorbs, could shift in response to these gases, affecting temperatures across the surface or any potential subsurface oceans. The very chemistry of K2-18b's atmosphere could, in turn, influence its climate, its weather patterns, and the potential for life-sustaining processes. Despite these compelling observations, methane alone is not a guarantee of life. On Earth, methane is generated in various ways. Volcanic outgassing, for instance, releases methane into the atmosphere without any biological processes involved. Hydrothermal vents deep beneath the oceans also produce methane, along with other compounds. In the case of K2-18b, however, it is the presence of both methane and carbon dioxide that raises eyebrows. This is a configuration not commonly seen in the atmospheres of gas giants like Jupiter or Saturn. An atmosphere rich in hydrogen, methane, and carbon dioxide are highly unusual, suggesting an interplay of forces unlike anything we've encountered before. More intriguing still is the role of hydrogen in this cosmic dance. As a solvent and chemical buffer, hydrogen plays a crucial role in shaping the planet's atmospheric dynamics. When combined with methane and carbon dioxide, it could be contributing to a feedback loop, regulating the behavior of these gases in ways that remain poorly understood. This chemical triad, methane, carbon dioxide, and hydrogen, may form part of a delicate balance that sustains the planetary atmosphere, an atmospheric harmony that hints at processes we have yet to fully comprehend. As scientists probe the mysteries of K2O-18b's atmosphere, the presence of methane and carbon dioxide together offers a tantalizing clue. This disequilibrium, the simultaneous presence of gases that would typically react with each other, points to something actively maintaining this state. On Earth, this would almost certainly be life. Could K2O-18b, in its far-flung corner of the galaxy, be hosting life or lifelike processes? Or is this an entirely novel form of planetary chemistry? The JWST's ability to measure these molecular interactions provides a unique opportunity. For the first time, scientists aren't simply detecting individual molecules. They are observing how these molecules relate to one another, how they function together as part of a larger system. By measuring the delicate balance of methane, carbon dioxide, and hydrogen, we get a glimpse of the planetary chemistry, in context, a snapshot of an alien atmosphere that could harbour life, or might simply be following an unknown, non-biological process. This new approach shifting our focus from simply detecting molecules to understanding how they interact could profoundly alter our understanding of what makes a planet habitable. Are the conditions on K2O-18b indicative of life as we know it? Or do they challenge our fundamental assumptions about how life might manifest elsewhere? These molecular interactions do more than just paint a picture of the atmosphere. They suggest a dynamic, evolving process, perhaps a cosmic dance that could mirror the early chemical pathways of life on Earth, or reveal an entirely novel form of existence beyond our current grasp. As we examine these interactions, we are forced to confront the very nature of life itself. What if the conditions for life are more flexible, more diverse than we ever imagined? In this context, methane and carbon dioxide transcend their role as mere indicators of atmospheric composition. They are the first whispers of a deeper, more intricate story, one that scientists are only beginning to unravel. This story raises profound questions that stretch beyond the confines of chemistry. Could the presence of these gases be telling us something about the fundamental nature of life itself? As we peer into the chemical signatures of K2O-18b, we must ask, are we truly alone in the universe, or is life perhaps in forms we've yet to recognize more widespread than we ever dared to imagine? This discovery forces us to reconsider the boundaries of life, challenging the very definition of what life might be and where it could exist. As the data from JWST continues to stream in, the mystery of K2O-18b deepens. The delicate balance of gases in its atmosphere challenges the very boundaries of what we think we know about habitability. With every new observation, scientists are peeling back another layer of the planet's secrets, moving us closer to understanding whether K2O-18b might be a home to life, or if it is simply a world of remarkable chemical processes we've never before encountered. Testing alternative explanations. The discovery of dimethyl sulfide DMS in the atmosphere of K2O-18b was nothing short of extraordinary. Scientists were faced with a tantalizing possibility. This organic molecule, typically linked to biological processes on Earth, might be a sign of life or some other unfamiliar process on an alien world. However, the scientific community's response was one of healthy skepticism, as such discoveries often carry with them the potential for misinterpretation. Such a groundbreaking finding demanded rigorous testing and scrutiny. Could this DMS have formed through non-biological, abiotic mechanisms? To answer this, the research team set out to explore various alternative explanations, hoping to rule out non-living causes before embracing the possibility of life. They recognized the immense importance of investigating all potential non-biological mechanisms thoroughly before considering a biological explanation. One of the first hypotheses to be explored was volcanic outgassing. On Earth, volcanoes spew a wide range of gases into the atmosphere, including methane, carbon dioxide, and hydrogen sulfide, and potentially even DMS. Could K2-18b's internal geochemistry replicate this volcanic process and produce DMS in a similar way? The researchers set to work building planetary models to simulate volcanic activity on this alien planet. They modeled plumes of sulfur-rich gases, including DMS, being released into the planet's hydrogen-heavy atmosphere. The goal was to calculate the expected spectral signatures from these plumes and compare them with the data gathered by the James Webb Space Telescope, JWST, which provided detailed and unprecedented views of K2-18b's atmosphere. This comparison was essential for confirming or ruling out volcanic activity as a source of DMS, which could give important clues to the planet's geochemical processes. The results were clear-cut. The simulated DMS from volcanic outgassing produced a much weaker signal than the one detected by JWST. The spectral features did not align with the observed data. Rather than the expected sharp DMS signature, the modelled plumes revealed a different set of molecules at slightly shifted wavelengths. This conclusive mismatch ruled out volcanic outgassing as a plausible cause for the DMS observed on K2-18b. The team's initial hypothesis had now been disproven, and they were one step closer to uncovering the true origin of the mysterious chemical signal. With volcanic outgassing no longer a viable explanation, they began to look more closely at other potential mechanisms, each requiring more detailed simulations and analyses. Turning their attention to a second possibility, the team considered photochemistry. Photochemistry occurs when ultraviolet UV radiation from a star breaks apart molecules in a planet's atmosphere, resulting in the formation of new chemical compounds. On Earth, photochemical reactions can generate a range of organic molecules, and researchers wondered if something similar might be occurring on K2-18b. The only problem? K2-18 is a red dwarf star, which emits relatively low levels of UV radiation compared to our Sunday. Would this lower flux of UV light be sufficient to drive the photochemical reactions needed to create DMS? This posed a significant challenge to the hypothesis, as it was unclear whether the amount of radiation from K2-18 would be powerful enough to break apart molecules and produce DMS through photochemical means. This hypothesis also faced significant challenges. The simulations revealed that the pressures necessary to produce DMS-like compounds from hydrogen oceans were much higher than those expected for K2-18b's atmosphere. The required temperatures also conflicted with the observed atmospheric gradients. These conditions were not supported by the current models of K2-18b's environment, ruling out hydrothermal vent chemistry as a plausible explanation for the DMS signal. Photochemistry, despite being a promising avenue, also failed to explain the data conclusively, suggesting that the cause of the DMS could lie elsewhere. This led the team to dig deeper into alternative hypotheses that might fit better with the conditions on K2-18b. With volcanic outgassing and photochemistry ruled out, the team turned to a third possibility: hydrothermal vent-like processes. On Earth, deep ocean hydrothermal vents are home to rich ecosystems that rely on sulfur-based chemistry. In these extreme environments, high pressures and temperatures support a variety of chemical reactions that create compounds like DMS. Could K2-18b, with its hydrogen-rich atmosphere and potential deep oceans, be hosting similar chemistry? The team modelled a scenario where deep hydrogen oceans interacted with the planet's atmosphere in ways that might produce DMS-like compounds, similar to the chemistry occurring at Earth's deep-sea vents. These environments on Earth are known to host ecosystems based on sulfur compounds so the team hoped that a similar phenomenon could be present on K-18b. This hypothesis also faced significant challenges. The simulations revealed that the pressures necessary to produce DMS-like compounds from hydrogen oceans were much higher than those expected for K-18b's atmosphere. The required temperatures also conflicted with the observed atmospheric gradients. These conditions were not supported by the current models of K-18b's environment, ruling out hydrothermal vent chemistry as a plausible explanation for the DMS signal. Once again, the team found that a seemingly promising hypothesis was not sufficient to explain the complex chemical signature they had observed. As they ruled out each possibility, the complexity of the problem deepened, but the search for answers continued relentlessly. By now, the research team had tested 3 major abiotic mechanisms: volcanic outgassing, photochemistry, and hydrothermal vent chemistry, and ruled each one out. The findings were clear. None of these processes could explain the intensity, clarity, or spectral profile of the DMS detected by JWST. While an unknown chemical pathway remained a possibility, the models increasingly pointed toward a biological, or at least biochemically analogous source for the dimethyl sulfide. The team recognized that this was a profound discovery. Though they could not yet definitively confirm life on K-18b, the failure of abiotic explanations led them to seriously entertain the idea that biological processes, or something similar to them, might be responsible for the DMS signal. This thorough process of testing alternative explanations reflects a key principle in exoplanet science. Extraordinary claims require extraordinary scrutiny. Each hypothesis, whether volcanic activity, photochemistry, or hydrothermal vent chemistry, was carefully tested against the available data. The results were not a simple yes or no. They involved a complex interplay of factors like temperature, pressure, radiation, and chemistry that must all be carefully analysed in context. As the team worked through these possibilities, they encountered an important insight. The search for life or lifelike processes is anything but straightforward. The interplay of complex variables meant that each theory had to be examined with the utmost care, and the conclusions were not always clear-cut. The team's exhaustive testing revealed a sobering truth. Even the strongest signals must be carefully dissected, questioned, and re-questioned. The DMS detected on K-18b could represent an entirely novel biochemical signature, or it could point to an unknown chemical process we've never encountered. The fact that none of the known abiotic mechanisms could explain it only adds to the mystery. K-18b may not be a world with life as we understand it, but it is undoubtedly a world with extraordinary chemistry so complex that it mirrors the processes we associate with life itself, even if not directly biological. This rigorous exercise in testing alternative explanations provides a valuable lesson for the future of exoplanet exploration. It underscores the importance of remaining open to a wide range of possibilities while maintaining rigorous skepticism. The signals we observe in distant worlds are not isolated, straightforward markers. They exist within a web of chemical and physical contexts that must be meticulously untangled. This careful approach is crucial if we are to understand the true nature of these distant planets and, perhaps, the very nature of life beyond our own world. Instrumental calibration and error control. The James Webb Space Telescope, JWST, stands as one of the most advanced scientific tools ever built, a testament to decades of innovation. However, even the most cutting-edge instruments come with their challenges. The faint, elusive signature of dimethyl sulfide, DMS, detected on K-18b was not immune to the quirks of the telescope's detectors. Cosmic rays, which constantly bombard the telescope as it orbits the Earth, can leave transient streaks in the data. These cosmic streaks can interfere with observations, momentarily distorting the spectral signals that are being captured. Then there's the issue of persistence sometimes. Signals from previous observations can linger, creating background noise that interferes with fresh data. To complicate matters further, the telescope's instruments can experience subtle shifts in sensitivity as they undergo thermal drift over time, meaning the same object might appear slightly different hours after the initial observation. Given that dimethyl sulfide is a faint spectral feature in the atmosphere of an exoplanet, this type of instrumental noise could easily mask or distort any potential signals. The discovery of DMS on K2O-18b, however, demanded a level of precision and error control that went well beyond the routine calibration checks. The team working on the detection of this molecule had to be certain that the signal they were observing was not just an artifact of the instruments. This required a sophisticated approach to separating the planetary signal from the noise introduced by the JWST's detectors. To do so, the team turned to advanced cross-correlation algorithms. These algorithms compare multiple datasets gathered across different transits of K2O-18b, often spaced months apart. By analysing the data from several distinct observations, the researchers were able to confirm that the DMS signature persisted consistently across all of them. If the signal had been a fluke or the result of an instrumental anomaly, it would have vanished in subsequent transits. But the persistence of the signal over time was an early victory in the fight to separate science from noise. The Bayesian approach is critical because it quantifies the uncertainty inherent in every measurement, offering a more transparent view of the data. By addressing the uncertainty, the team could say with greater confidence that the signal wasn't a coincidence. When they applied this method, the result was striking. The confidence level reached 3 sigma, meaning there was a 99.7% probability that the detected signal was genuine, a key step in ensuring the validity of their discovery. However, even this high degree of confidence wasn't enough to draw final conclusions. Independent verification of the data was essential, because even the most advanced models can't account for every possible error. In early 2025, the raw JWST data for K2O-18b was reprocessed at NASA's Goddard Space Flight Center. This step was crucial. The team there recalibrated the detector's dark currents background signals that can introduce unwanted noise into measurements. They also corrected for spectral flat field errors, which distort how light is absorbed by the instrument. Even small changes in the pointing of the telescope can affect the accuracy of the data, so the team had to account for any minor drifts in the telescope's alignment during the observations. Each of these calibration steps was necessary to ensure that the signal was not being skewed by external factors. The recalibration process was not simply about fixing errors, it was about confirming that the DMS signal could still be identified after every potential source of noise had been addressed. After all these rigorous recalibrations, the DMS signal remained unmistakably present. It wasn't just resilient, it was robust. This was a key moment in the validation process. It meant that the signal was not a fluke of the system, but an actual feature of the planet's atmosphere. But even then, the team knew that independent validation would still be crucial to the integrity of their findings. To solidify their confidence in the detection, the researchers turned to ground-based laboratories. These laboratories had collected spectra of DMS and dimethyl disulfide, DMDS, in controlled environments that mimicked the conditions of hydrogen-rich atmospheres. Such controlled experiments allowed the scientists to create a database of spectral fingerprints that closely mirrored the chemical interactions expected on exoplanets like K2O-18b. The lab spectra were carefully compared with the data from the JWST, confirming that the features they had observed were consistent with known DMS signatures under those atmospheric conditions. Temperature, pressure, and molecular composition all play a role in shaping the absorption bands that JWST detects, and ensuring that the laboratory conditions matched those of K2-18b's atmosphere was essential. These reference spectra were invaluable because they allowed the researchers to rule out other potential compounds that might have interfered with the DMS signal. The process wasn't just about confirming that DMS existed, it was about eliminating every other possible source of error. It was a painstaking task, but one that allowed the team to separate valid scientific discoveries from the noise of the instruments, providing a clear signal that could be traced back to a specific molecular compound in an alien atmosphere. In a sense, the entire process was like conducting an experiment in a cosmic laboratory. JWST, with all its incredible power, serves not just as a telescope, but as a precision instrument, with every photon captured, analysed, and interpreted. To ensure the utmost accuracy, the team had to account for every potential error, recalibrating each aspect of the system until they were certain that the chemical makeup of K2-18b's atmosphere was not a product of faulty instrumentation. Only after such exhaustive corrections and cross-checks could they confidently say that the signature they had observed was likely to be DMS, a molecule that, on Earth, is typically produced by biological processes, a molecule that may also hint at the possibility of life beyond our planet. The entire process underscored the importance of careful, methodical science. In the search for life beyond Earth, even a 3 sigma result is treated with excitement, but also with caution. After all, the discovery of DMS could suggest the presence of life or biological-like processes on K2-18b, but without exhaustive calibration and error correction, no claim can be made definitively. The meticulousness of the process serves as a reminder that the universe may hold answers, but those answers must be uncovered through rigorous, careful work, always mindful of the uncertainties that persist. Every calibration, every correction, every independent check brings us closer to understanding what lies beyond our solar system. As the data streams in from the JWST, we can be certain that each photon of information is being handled with the highest standards of precision, moving us ever closer to answering some of the most profound questions about life in the cosmos, questions that may one day redefine our place in the universe. The planetary system context. K2-18b exists within a dynamic planetary system, but understanding its potential habitability requires a deeper look at the context in which it resides, its host star, nearby planets, and the delicate balance of conditions that make life possible. K2-18, a red dwarf star located 124 light-years away in the constellation Leo, serves as the primary source of energy for its orbiting planets. Red dwarfs are the most common type of star in the universe, but their dimness and volatility pose challenges for planets seeking to sustain life. K2-18 is no exception, with a mass of about 0.49 times that of the Sun and a surface temperature hovering around 3,500 Kelvin. Its luminosity is just 2.4% of the Sun's, which means any planets in its system must orbit close to the star to receive enough energy for liquid water to exist, one of the crucial ingredients for life as we know it. Unlike many other red dwarfs, K2-18 has a relatively calm temperament. Red dwarfs are notorious for their intense flaring activity, which can release vast amounts of radiation, strip away planetary atmospheres, and potentially making surface conditions hostile to life. Flares are common among these stars, often occurring on timescales that can have dramatic consequences for nearby planets. However, K2-18 is notably more stable, with flares that are infrequent and not as intense as those of its more active counterparts. This stability is a critical factor in understanding the planet's potential to harbour life. If flares were more common or more powerful, they might strip away any atmosphere K2-18b might have, or disrupt the chemical processes necessary for life. The relative calm of K2-18 increases the chances that atmospheric molecules like the dimethyl sulfide, DMS, signature observed on K2-18b, can survive without being obliterated by energetic stellar radiation. Within the K2-18 system, there is at least one other planet, K2-18c. This planet orbits much closer to its star, completing a full orbit every 9 days. Its proximity means it likely experiences intense heat, making it tidally locked. One side of the planet always faces the star, while the other remains in perpetual darkness. The extreme temperatures on K2-18c rule out the possibility of liquid water, putting it outside the star's habitable zone. The heat and radiation it receives are so intense that any chance of sustaining life would be minimal, at least in any form we recognize. In contrast, K2-18b sits in a far more promising position. Orbiting its star once every 33 days, it lies at about 0.14 astronomical units from K2-18, comfortably within the star's habitable zone. This is the region where temperatures are just right, not too hot and not too cold for liquid water to exist on or beneath the planet's surface. While the specific conditions on K2-18b are still under study, the mere fact that it orbits within this zone means it could potentially offer a stable environment where the building blocks of life could form and persist. Planetary formation models suggest that K2-18b likely began its life by accreting a significant envelope of hydrogen early on. This is typical for planets of its size. With a radius between that of Earth and Neptune, K2-18b is large enough to retain thick atmospheres, which is important for providing a buffer against stellar radiation and preserving any chemical processes that may occur on the surface or in the deeper layers of its atmosphere. While its size allows it to hold onto this hydrogen envelope, it's not so massive that it would be classified as a gas giant. Instead, K2-18b is considered a sub-Neptune type planet, a size category between Earth and Neptune that allows for the possibility of a global ocean beneath the thick, hydrogen-rich atmosphere. This internal ocean could harbour the right conditions for life to form, or at the very least provide a medium for complex chemistry to unfold. The planet's ability to maintain a thick atmosphere is key in understanding its potential for habitability. If K2-18b were orbiting too close to its star, the energy from K2-18's radiation would be far too intense, possibly stripping away the atmosphere and leaving the planet with no protection against the star's harsh environment. On the other hand, if K2-18b were too far from the star, temperatures would plunge, making liquid water impossible. But K2-18b occupies a rare and precious sweet spot, close enough to its star to maintain temperate conditions, yet far enough to avoid being subjected to the devastating effects of flaring or excessive radiation. This delicate balance also makes K2-18b an ideal candidate for studying how biosignatures, signs of life, or biological-like processes might be preserved. In planetary science, it's well understood that planets in the habitable zone have a much higher chance of maintaining conditions conducive to life. But not all habitable zone planets are created equal. A planet in an unstable orbit or subject to frequent stellar flares may be unable to sustain an atmosphere long enough for complex molecules to form and persist. Likewise, a planet too far from its star may be too cold for liquid water, even if its atmosphere is stable. K2-18b's location in this narrow zone, combined with the relative calm of its star, offers a unique opportunity for scientists to study how long-term habitability might unfold. In the broader context of its system, K2-18b is an intriguing outlier. Most stars with planets in the habitable zone tend to be more active than K2-18, and many of the known exoplanets in these zones are around stars that exhibit much higher levels of radiation. The fact that K-18 is relatively quiet gives K-18b a distinct advantage. It allows scientists to hypothesize that the planet's atmosphere, potentially rich in gases like DMS, might have been shielded from destruction long enough for such molecules to accumulate, perhaps even to levels detectable by telescopes like the James Webb Space Telescope. By placing K-18b within the context of its planetary system, scientists can refine their models of habitability. Its relative position in the habitable zone, coupled with the stability of its star, creates a favorable environment for chemical processes, possibly even for life, or at least lifelike processes to emerge. Each of these factors, planet size, atmospheric retention, orbital location, plays a critical role in understanding not only the planet's current state, but its potential for future discovery. It's not just K-18b itself that has captured the attention of astronomers, but the system as a whole. The presence of K-18c, a tidally locked planet too hot for life, provides additional context. It demonstrates the range of conditions that can exist in a system and how subtle differences in distance from the star can have profound effects on habitability. Together, these planets offer a view into how complex and varied exoplanetary systems can be, each planet an individual piece in the puzzle of cosmic habitability. In this distant corner of the universe, 124 light-years away, the JWST has begun to explore one such planetary system. Within this system, K-18b stands out as a potential site of interest, offering clues about the chemistry that could support life. As observations continue, scientists will gather more data on its atmospheric composition, orbital characteristics, and environmental conditions, helping to refine our understanding of exoplanetary systems. How JWST reads biosignatures. When the James Webb Space Telescope JWST peers into the depths of space, it's not snapping pictures of alien life. Instead, it's revealing the hidden signatures of distant worlds, chemical imprints left behind in the light from stars. On a planet like K-18b, for example, this process unfolds during every transit, when the planet passes in front of its host star. As the star's light filters through the planet's atmosphere, molecules in that atmosphere absorb specific wavelengths of light, creating distinct absorption lines in the spectrum. These lines tell a story, a chemical story. At the heart of this story is JWST's near-infrared spectrograph, NIRSpec, an instrument capable of splitting incoming starlight into thousands of narrow, precisely defined wavelength bins. These bins reveal subtle dips in the spectrum, each one corresponding to a molecule. Think of it as reading a barcode, where each dip corresponds to a different chemical fingerprint. The presence of methane, carbon dioxide, or dimethyl sulfide, DMS, on a distant exoplanet can be identified this way. And for planets like K-18b, these signatures are critical. DMS in particular is a molecule often linked to biological activity on Earth, making its detection a potential clue for life. But capturing these tiny spectral shifts isn't as simple as pointing a telescope and waiting for results. The light coming from distant stars is often drowned out by the star's intense glare, and small noises like cosmic rays or thermal drift can blur the data. That's where JWST's precision comes into play. To separate the faint planetary signal from the noise, JWST employs sophisticated cross-correlation algorithms. These algorithms allow scientists to compare data across multiple transits, sometimes spaced months apart, ensuring that any signature they detect is consistent and reliable. It's not just about identifying a signal, it's about verifying it. And for that, JWST's Bayesian retrieval models come into play. These models calculate the likelihood of a particular molecule being present, giving researchers a statistical confidence level that informs their analysis. The goal is to produce data that can be consistently verified and withstand the scrutiny of independent analysis. In the case of K2-18b, these verifications went a step further. The raw data collected by JWST were reprocessed by NASA's Goddard Space Flight Center in early 2025. This process involved recalibrating the detectors, correcting for errors like spectral flat field distortions, and accounting for any minor drifts in the telescope's pointing. After these corrections, the DMS signal remained strong, adding another layer of confidence to the discovery. This kind of rigorous error control ensures that what scientists are seeing is not a byproduct of instrumentation, but an accurate representation of the planet's atmosphere. While JWST's internal calibration is critical, it's not the only step in ensuring that its findings are reliable. The team also turned to ground-based laboratories for verification. Laboratory spectra of DMS and other similar compounds, collected under conditions mimicking the hydrogen-rich atmospheres of distant planets, were compared with the data from JWST. These laboratory measurements were crucial because the absorption lines of molecules like DMS are sensitive to temperature, pressure, and other atmospheric factors. By comparing the observed spectral features with laboratory measurements, scientists confirm the authenticity of the detected features. At the core of this process is a level of precision that makes JWST an unparalleled tool for studying distant planets. The telescope's instruments don't just detect light, they transform it into a chemical analysis, offering a detailed snapshot of the planet's atmosphere. Each molecule's unique absorption pattern adds a new layer to the puzzle, enabling scientists to infer the chemical makeup of a distant world without ever visiting it. This approach is far more than just about detecting life. It's about mapping out the very fabric of planetary atmospheres, and JWST's ability to detect even the faintest signals doesn't stop there. The Near-Infrared Imager and Slitless Spectrograph, NIRIS, provide additional precision. NIRIS allows for the detection of smaller absorption features that could otherwise be lost in the noise. Even when the signal is weak, this instrument helps to pull out the details needed to confirm molecular signatures, providing another layer of reliability to the data. Beyond NIRSPEC and NIRIS, JWST's mid-infrared instrument, MIRI, extends the wavelength coverage into the mid-infrared range. This opens up a whole new window for detecting molecules that absorb at longer wavelengths, such as ammonia or nitrous oxide, molecules that are often linked to biological processes on Earth. MIRI enables astronomers to expand their search for biosignatures, detecting molecules that may not be visible in the near-infrared spectrum. These instruments, NIRSPEC, NIRIS, and MIRI, are the tools that turn a stream of photons into a narrative about distant worlds. And the process isn't just about identifying molecules, it's about understanding the broader chemical context in which they exist. Are the molecules detected consistent with biological activity? Or could they be the result of geological or chemical processes? That's the crux of the analysis. Each molecule's spectral signature is analysed to determine whether it corresponds to expected patterns or could result from non-biological processes. The sophistication of JWST's instruments allows for the kind of detailed analysis that was once impossible. By capturing the faintest absorption features and comparing them to laboratory data, scientists can make far more accurate predictions about the chemical makeup of distant planets. This enables researchers to build a picture of a planet's atmosphere and determine whether it has the conditions necessary for life, or at least for lifelike processes. What makes this approach so powerful is the level of detail it offers. Every piece of data, every tiny shift in the spectrum, is a clue. The DMS signature observed on K2-18b is just one example of how JWST is transforming our understanding of distant exoplanets. Each new observation provides valuable insights into the chemical makeup of these worlds, contributing to our understanding of their atmospheres. And the best part? JWST is only getting started. As more data comes in, scientists will continue to refine their models, improve their techniques, and push the boundaries of what we can learn about distant exoplanets. The detection of potential biosignatures on distant planets is now a reality, thanks to JWST's ability to analyze the chemical signatures in starlight. Data released to the public on the 16th of April 2025, a monumental shift in the world of exoplanetary science took place. The James Webb Space Telescope, JWST team, made its K-18b observations available to the global scientific community. The data was released through key platforms, including the European Space Agency, ESA, NASA's Exoplanet Science Institute, and the Mikulski Archive for Space Telescopes, MAST, providing unprecedented access for researchers worldwide. With this release, scientists from all corners of the globe could now dive into the raw spectra, calibration files, and Bayesian retrieval analyses that had so far been closely guarded. This openness ensured that the findings could be verified, scrutinized, and, most importantly, built upon by independent teams. At the heart of this dataset was the persistent signal of dimethyl sulfide, DMS, a molecule that could hold profound implications for astrobiology. The release included the raw spectral data from JWST's NIRSpec and NIRIS instruments, both of which had captured the absorption features indicative of DMS in the atmosphere of K-18b. Also included were Bayesian retrieval results, providing estimates on the likelihood that specific molecules were present in the atmosphere, as well as their vertical distribution and abundance. This data was rich with information, from spectral fingerprints of potential biosignatures to detailed atmospheric conditions. For K-18b, the key takeaway was the repeated detection of DMS across multiple transits. This finding was groundbreaking. It not only confirmed the presence of a potential biosignature, but also bolstered the idea that K-18b might harbor the right conditions for life, or at least lifelike processes, to occur. Within hours of the data release, the scientific community went into overdrive. Independent research teams immediately began cross-checking the results. One of the first areas of scrutiny was stellar contamination. Could the star's activity, such as flares and radiation, be contaminating the signal and mimicking the DMS absorption features? A team of astronomers focused on verifying that the signal was genuinely coming from K-18b's atmosphere and not from the star itself. They analyzed the data in finer detail, running simulations to account for the possibility of stellar flaring affecting the spectral data. Other teams focused on rerunning the retrieval algorithms, adjusting parameters, and fine-tuning models to confirm the robustness of the DMS signal. All these steps were crucial in ensuring that the initial results weren't just coincidental or the product of observational noise. Within weeks, the hard work of independent teams paid off. The results were in. After rigorous validation, the DMS signal remained intact. The absorption feature persisted through various analyses, reinforcing the confidence that the signal wasn't an artifact of the data or the instruments. The 3 sigma confidence level, meaning the likelihood that the signal was genuine and not due to random chance, held firm. What began as a groundbreaking observation had now gained widespread confirmation, adding to the excitement and intrigue surrounding K-18b. The global collaboration between independent researchers ensured that the findings were reliable, replicable, and robust. The persistent DMS signal wasn't just a blip, it was a consistent, verifiable feature that couldn't be easily dismissed. The release of the K2O-18b dataset exemplifies the growing trend in modern astronomical research toward greater transparency. In a field where data can be elusive and discoveries hard-earned, making raw data publicly accessible accelerates the pace of discovery. By releasing the data to the public, the JWST team created a global scientific laboratory that anyone, anywhere, could access and contribute to. This openness didn't just allow other scientists to verify the findings, it enabled them to build upon it. Researchers could now run their own models of high sea and atmospheres, a proposed class of planets with hydrogen-rich atmospheres and liquid water, biosignature chemistry, and climate processes. They could refine their understanding of how life might emerge on distant worlds and what biosignatures might look like. The K2O-18b dataset wasn't just an isolated set of observations, it became a resource for advancing the science of exoplanet habitability. This transparency accelerated discovery. Scientists in universities, research institutions, and private labs around the world began to explore the data, testing hypotheses and running simulations. Some focused on refining the atmospheric models, considering how water might exist in the planet's atmosphere or beneath its surface. Others explored the potential for DMS to exist without biological processes, considering non-biological origins for the molecule. Yet others worked on refining atmospheric models, incorporating the latest research on exoplanet climatology to understand how K2O-18b might support liquid water despite its hydrogen-rich atmosphere. By making the data publicly available, the JWST team allowed researchers from various institutions to contribute to interpreting the finding. Instead, the entire world could participate in the analysis, each researcher bringing their own expertise to the table. This process transformed K2O-18b's discovery from an isolated observation into a global scientific endeavor, a collective effort where everyone contributed, shared, and debated their interpretations. The entire scientific community was now part of the conversation, testing, and refining theories as the story of K2O-18b continued to unfold. The approach extended the research timeline beyond the initial team's involvement, allowing for ongoing analysis. A discovery that might have been confined to a few months of intense study was now an ongoing effort. Researchers could go back to the data at any time, using new algorithms, computational tools, and insights to revisit and reevaluate the findings. The dataset wasn't static, it was dynamic, providing new opportunities for insight and discovery with each new piece of information and each new approach. The public release of the K2O-18b data marked a shift in how astronomical discoveries are shared and analysed. It was no longer just about a handful of researchers uncovering the secrets of the universe. It was about the entire scientific community, regardless of location or funding, working together toward a common goal. The K2O-18b dataset became a catalyst for collaboration, debate, and ultimately deeper understanding. As new data came in, as new discoveries were made, the excitement surrounding the potential for life beyond Earth only intensified. And as researchers around the world continued to analyze and refine their understanding of K2O-18b, it became clear that the search for life on exoplanets was no longer confined to theoretical models. It had entered a new empirical phase. With the data now accessible to scientists globally, the potential to study K2O-18b's atmosphere and its relevance to life processes became a collective effort. The release wasn't just a milestone, it was the beginning of a new chapter in the study of distant worlds. The statistical threshold ahead, the 3 sigma confidence level in the detection of dimethyl sulfide DMS on K2O-18b indicates a significant finding, suggesting that a notable chemical signature might be present on this distant world. However, while this finding is significant, it is not the final confirmation of biological or lifelike processes on an exoplanet. In the world of astrophysics, even extraordinary discoveries like this one require extraordinary evidence. And while a 99.7% probability might seem robust, it's far from the gold standard in science. To truly settle the question, a 5 sigma confidence level is required, a near-perfect certainty of 99.99994%. At this level, any lingering doubts about random fluctuations, instrumental noise, or systematic errors would be all but eliminated. Achieving 5 sigma confidence isn't just a matter of conducting more observations. It's about ensuring that the data is irrefutable, and that's where the next phase of the James Webb Space Telescope JWST mission comes in. The next observation cycle, scheduled from late 2025 through mid-2026, will focus on K2-18b with a dedication that matches the stakes. A full 20 hours of observation time has been set aside to capture additional spectra, covering the critical 1.5 micrometer wavelength range and extending into the mid-infrared with JWST's MIRI instrument. These observations aren't just an opportunity to reinforce the existing data, they're an opportunity to elevate the evidence to the level of certainty required for a breakthrough in astrobiology. The stakes for this follow-up research are high, as the team has several clear objectives. First and foremost, they aim to increase the detection significance of the DMS signal from 3 sigma to the coveted 5 sigma. This would provide a much higher level of confidence that the signal isn't just a transient anomaly or random fluctuation, but something real and persistent. To do so, the researchers will track K2-18b through multiple transits, each one providing another snapshot of the planet's atmosphere. As more data pours in, the statistical weight of the evidence will increase, and the likelihood that the DMS signal is real will grow stronger. Confirming the DMS signal is an important goal, but it is just one part of a broader scientific mission. The follow-up observations will also focus on ensuring that the DMS signal is not just persistent, but reproducible. This is a crucial step. If the signal is real, it should appear consistently across several transits, unaffected by the typical noise or contamination that can occur in these types of observations. Only then will scientists be able to confidently claim that they've detected a molecule that might be associated with biological processes. If the signal disappears or fluctuates erratically, it could cast doubt on the previous findings, and the team will need to reassess. In addition to focusing on DMS, the JWST team will also expand their search to include other molecules that could strengthen the biological interpretation of the data. Molecules like ammonia NH3 and nitrous oxide N2O, which have been associated with biological processes on Earth, will be prime candidates for detection. The presence of these molecules alongside DMS could strengthen the hypothesis that K2-18b's atmosphere contains chemical signatures potentially linked to life. These complementary biosignatures, when detected together, could serve as powerful evidence for life or lifelike processes occurring on the exoplanet. Bayesian retrieval models and cross-correlation analyses will once again be at the heart of the study. But with a larger dataset and higher resolution observations, scientists will have a much clearer view of the atmospheric composition. The uncertainty in molecular abundances will shrink, allowing for more precise calculation. The refined data will help researchers better understand the planet's atmospheric chemistry, how it evolves, and how it could sustain life. More importantly, these models will help elucidate how hydrogen-dominated atmospheres, like the one suspected to exist on K2-18b, might function in ways that could support habitability. Understanding these atmospheric dynamics will not only provide insight into K2-18b, but will also inform our broader search for life elsewhere in the universe. For scientists, this upcoming observation cycle is a crucial step in the research process. where the possibility of detecting biological signatures could become more concrete. If the DMS signal holds steady and complementary molecules are detected, K2-18b could go from being a candidate Hycean world with probable life to becoming the first confirmed exoplanet with atmospheric molecules most likely produced by living organisms. It would represent a paradigm shift in how we think about the potential for life beyond Earth and how we detect it. The stakes are immense, and the pressure to deliver results is even higher. As the late 2025 observation cycle approaches, each photon captured by JWST will contribute to a more detailed understanding of the planet, either supporting or refining current findings. The potential of what they're about to uncover is as thrilling as it is daunting, but the methodology behind it all remains rigorously scientific. The world will watch, and the scientific community will scrutinize each new data point with the kind of precision that only modern astrophysics can offer. Each observation, each spectrum, each analysis will inch us closer to understanding whether K2-18b is just another distant world or a harbinger of something far more profound. The next series of observations will contribute to the growing body of evidence for exoplanetary science and help refine what can be confidently claimed about distant planets. The 5 sigma confidence level represents the threshold at which the question of life on K2-18b can be answered with statistical certainty, and that is the moment that everyone in the field of astrobiology is eagerly awaiting. Rewriting planetary habitability. The confirmation of dimethyl sulfide, DMS, on K2-18b would represent a significant shift in our understanding of planetary science. For decades, astronomers have focused their efforts on finding Earth-like planets, rocky worlds with temperate climates, oxygen-rich atmospheres, and seas of liquid water similar to the conditions that support life on Earth. The discovery of DMS, a molecule linked to biological processes on our planet, challenges this narrow focus. K2-18b's peculiar atmosphere and its potential to support life open up new possibilities for what constitutes a habitable world in the cosmos. K2-18b, with its hydrogen-rich atmosphere and the likelihood of a global ocean beneath intense pressure, belongs to a class of planets known as Hycean worlds. These planets, composed largely of hydrogen and water, may be much more common in the galaxy than previously thought. Red dwarf stars, which are the most abundant type of star in the Milky Way, frequently host planets like K2-18b. If life can exist in such an environment, it forces us to reconsider the traditional criteria for habitability. The discovery could suggest that life is not confined to rocky planets like Earth, but could thrive in radically different conditions. Hycean planets are massive enough to retain thick atmospheres and potentially harbour oceans that remain stable despite the extreme pressures and temperatures. K2-18b, orbiting its cool red dwarf star, sits at a distance where liquid water might exist beneath its dense, hydrogen-dominated atmosphere. This adds new dimensions to the search for habitable planets, where such environments must now be considered as potential candidates for life. It's a pivotal moment in planetary science, where the definition of habitable expands to include a new category of worlds that were previously overlooked. K2-18b's atmospheric composition offers new insights into the search for life. If dimethyl sulfide is a product of biological activity, it may indicate that life can influence the planet's chemical composition in ways similar to processes observed on Earth. On Earth, DMS is released by plankton and other microorganisms. If K2-18b's atmosphere shows similar disequilibrium molecules that would normally react with each other in a stable environment, but are maintained by biological processes, it would suggest that life could exist in a radically different chemical and physical context. Scientists would be able to study how life might modify the atmosphere of a planet that is so different from Earth, opening the door to understanding how life might emerge and sustain itself on other types of worlds. In addition to DMS, there are other molecular candidates that could point to biological activity. The presence of methane, carbon dioxide, or even ammonia could also provide important clues. These molecules, particularly in the quantities and ratios found in K-18b's atmosphere, could indicate that a biosphere is at work. Life forms on Earth have consistently altered the atmospheric composition of our planet, maintaining chemical balances that would otherwise shift toward equilibrium. By studying these chemical signatures in the atmosphere of K-18b, planetary scientists would gain new insights into how life might emerge, persist, and shape its environment on a Haitian world. However, the discovery raises further questions about planetary evolution. K-18b's unique environment invites deeper exploration into how a planet like it could maintain its ocean beneath a thick hydrogen atmosphere over billions of years. What mechanisms allow the planet to keep its atmosphere stable, and what forces sustain the pressure and temperature conditions that could allow liquid water to remain in a stable state? Scientists speculate that geothermal heat from the planet's interior or tidal forces from gravitational interactions with its host star might be at play, helping to keep the ocean and atmosphere intact despite the absence of direct sunlight. Understanding these mechanisms will be crucial in refining models of planetary habitability. K-18b also presents an opportunity to probe the boundaries of life itself. Could life arise in an atmosphere that is so different from Earth's, with high hydrogen pressures and potentially no access to sunlight? Could life exist below the ocean, sustained by heat from the planet's core or chemical energy from the planet's atmosphere? These are fundamental questions that extend far beyond K-18b. If the planet is capable of supporting life, it could revolutionize our understanding of what types of environments are capable of nurturing life. For astrobiology, K-18b provides a valuable test case for theories about the potential for life in the galaxy. The discovery of DMS would suggest that life could arise in environments that are vastly different from Earth. It would also open the possibility that other planets possibly located around red dwarf stars might harbour similar chemical signatures, providing a roadmap for future exoplanet missions focused on detecting biosignatures in alien atmospheres. This discovery also paves the way for future research into the chemical cycles and biogeochemical processes that may occur on Haitian worlds. If the planet's atmosphere is indeed shaped by biological processes, understanding how those processes operate in a hydrogen-rich environment could provide clues about how life on Earth first began. How did early Earth's atmosphere, so different from the one we have today, support the origin of life? And could other worlds, with their own unique environments, provide the same opportunities for life to emerge? K-18b's status as a potential Haitian world makes it a powerful tool for investigating the broader question of planetary habitability. The planet's strange and extreme conditions challenge everything we know about what makes a planet livable. If life is confirmed on K-18b, it will force a rethinking of how we categorize exoplanets, potentially leading to the recognition of an entirely new class of habitable worlds that do not fit neatly into the Earth-like paradigm. This would have significant implications for how we search for life elsewhere in the galaxy. Scientists are already expanding their search for similar worlds. With new telescopes and advanced instruments, the next generation of astronomers will scan the skies for more Haitian planets' worlds that challenge our assumptions about where life can exist. K-18b is just the beginning. The real excitement lies in the knowledge that this world could be the first of many, leading to a deeper understanding of the diversity of habitable environments in the universe. As researchers continue to analyze the data from K-18b, They are not just answering questions about one distant planet, they are laying the groundwork for a new era in planetary science. The discovery of DMS and the potential for life on a Hycean world would be one of the most significant breakthroughs in the search for extraterrestrial life. It would change the way we view planets, atmospheres, and the very nature of life itself. And it would set the stage for a new chapter in our exploration of the universe. A chapter where life is no longer defined by the conditions of our own planet, but by the boundless possibilities that exist across the cosmos. K2-18b, redefining the search for life. By October 2025, astronomers had catalogued over 5,600 confirmed exoplanets, ranging from colossal hot Jupiters to icy Neptunes, and small rocky worlds that resemble Earth. None of these worlds, despite their variety, had provided convincing evidence of biosignature gases until K2-18b. Located 124 light-years away, roughly 700 trillion miles, this distant world offers the first potential evidence of biology beyond our solar system. The detection of dimethyl sulfide, DMS, on K2-18b, confirmed with 3 sigma confidence, is a significant scientific discovery. For decades, the search for life has focused on planets similar to Earth rocky, with temperate climates and oxygen-rich atmospheres. K2-18b challenges this model, suggesting that life could exist in environments we have not previously considered, broadening our understanding of what constitutes a habitable world. K2-18b, with its thick hydrogen-rich atmosphere and potential for a global ocean beneath high pressures, challenges previous assumptions about where life could thrive. The discovery of DMS, a chemical compound often associated with biological processes on Earth, raises the possibility that life could exist on worlds vastly different from our own. With each new spectrum captured by the James Webb Space Telescope, JWST, we are gradually gaining insights into this question. This breakthrough highlights the critical role of the technology behind JWST. The telescope's advanced instruments, such as NIRSpec and MIRI, were key in detecting distant biosignatures. The precision required to capture such faint signals across 124 light-years is remarkable. Without JWST's sensitivity and resolution, the faint traces of DMS would likely have gone unnoticed, underscoring the collaborative efforts of scientists around the globe. The release of K2-18b's data didn't just answer questions, it raised new ones. What other biosignatures might be found in the atmospheres of distant worlds? The success of JWST in identifying DMS serves as a reminder that we are only at the beginning of this journey. Each new observation and dataset brings with it the potential to refine our understanding of life beyond Earth. K2-18b's faint signature is the starting point for exploring how life could manifest in diverse environments. This discovery shifts the focus of exoplanet research. For years, planetary scientists have concentrated on Earth-like planets, those within the habitable zone of their parent stars, where liquid water could exist. K2-18b, however, doesn't fit that mold. Its thick hydrogen atmosphere and potential ocean beneath immense pressure categorize it as a Hycean world, a type of planet that was largely theoretical until now. Hycean worlds like K2-18b may be more common than rocky, Earth-like planets, and could represent promising candidates for hosting life. These worlds expand our definitions of habitability, suggesting new models of atmospheric chemistry, ocean dynamics, and biological potential. For astronomers, K2-18b's potential biosignature is a tantalizing puzzle. The question isn't just about whether life exists there, it's about how we can definitively prove it. The coming years will see astronomers refine their techniques, using both JWST and future space telescopes to observe exoplanetary atmospheres with greater detail. The large UV divided by optical divided by Infrared Surveyor, LUVOIR, and the Origin Space Telescope, are just a couple of upcoming missions that will build on the findings of JWST, opening new frontiers in the search for life. With these instruments, scientists will push the limits of sensitivity, searching for new molecules associated with life. Could methane or ammonia coexist with DMS, as we might expect in a biological process? The answers to these questions may soon be within reach, but only through continuous observation and analysis. JWST's work on K2O-18b represents one part of the broader story of exoplanet exploration and discovery. The potential biosignature on K2-18b has significant implications not only for astrobiology, but for planetary science. If life can exist on a world vastly different from Earth, the definition of a habitable world broadens. We are no longer limited to the idea that life requires a specific set of conditions: water, an oxygen-rich atmosphere, and moderate temperatures. We must now consider planets with thick hydrogen atmospheres, intense pressures, and oceans beneath the surface as possible hosts for life. K2-18b prompts important questions. How adaptable is life? How far can it extend the boundaries of the environments it inhabits? And how many other worlds might share similar conditions? Moreover, K2O-18b's discovery highlights red dwarf stars, which make up about 70% of the stars in the Milky Way. These stars, often overlooked in the search for life due to their cooler temperatures and lower luminosity, may actually be far more significant than we previously thought. Their stability and long lifespan could provide ample time for life to develop on planets within their habitable zones. This realization shifts our perspective. Planets orbiting red dwarfs could harbor life, and their extended stability offers an opportunity for complex biosignatures to emerge. The discovery of DMS on K2O-18b suggests that life could be far more prevalent than we imagined, thriving in environments previously considered hostile. These insights might prompt a reconsideration of how we prioritize red dwarf stars in our ongoing search for biosignatures, potentially opening up vast new possibilities. The broader cosmic context of K2O-18b's discovery cannot be overstated. Once thought to be a barren and indifferent expanse, the universe now seems more inviting and alive with possibility. The discovery that life may exist, or could have once existed on another planet, turns the search for life into a practical and actionable endeavor. This shifts the conversation from abstract speculation to tangible science, bringing humanity one step closer to understanding our place in the vastness of the cosmos. We are no longer merely asking if life exists elsewhere. We are learning how to find it, armed with powerful scientific tools and methods. With each new detection, humanity's perspective grows closer to recognizing that we are not alone in our quest for knowledge. The dream of finding extraterrestrial life becomes increasingly tangible, reshaping the way we view our place in the universe. In the years to come, as JWST continues to uncover the secrets of the universe, one thing is certain: the search for life beyond Earth will never be the same. K2-18b may be the first of many discoveries that reveal the universe's vast complexity, diversity, and teeming potential. Each observation will build on prior breakthroughs, providing more insights into distant worlds than ever before. With technological advancements in observation and data analysis, we can now detect even the faintest biosignatures. The search is far from over. It's only just beginning, and with every new discovery, we move closer to understanding life in a broader, universal context. This new understanding could reshape our very concept of biology, expanding the limits of what we thought possible for life to exist across the universe.